What if everything you think you know about the universe is based on a set of rules that were never actually written down? Picture this: a cosmos where the fundamental laws of reality weren't predetermined or handed down from some higher authority, but instead emerged from a state of pure, chaotic possibility. A universe that essentially chose its own game, setting the parameters for existence through a process we're only beginning to understand. This isn't science fiction. This is one of the most profound mysteries at the heart of modern cosmology, a puzzle that challenges our very understanding of why things are the way they are. Consider the astonishing precision of our universe's physical constants. The strength of gravity, the force that holds galaxies together, the electromagnetic force that allows atoms to form and light to travel. The cosmological constant that determines how quickly space itself expands. Each of these fundamental values exists within razor-thin margins that make life possible. If gravity were slightly stronger, stars would burn out too quickly. If the electromagnetic force were weaker, atoms couldn't hold together. If the expansion rate were different, galaxies might never have formed at all. The odds of all these values aligning perfectly by chance are so astronomically small that it defies imagination, like throwing a dart across the observable universe and hitting a single predetermined atom. This remarkable fine-tuning raises questions that go straight to the core of existence itself. Was this perfect balance simply a cosmic accident, a lucky roll of the dice in an infinite multiverse, or does it suggest something more intentional, more profound at work? Over the course of this journey, we'll explore these competing theories, from the multiverse hypothesis to cosmic natural selection, from mathematical necessity to the possibility of simulation. We'll question whether our reality is the product of design, chance, or something even more extraordinary that we haven't yet imagined. Prepare to have your understanding of reality fundamentally transformed as we venture into the deepest mysteries of cosmic order, exploring why our universe seems to follow rules that appear too perfect to be accidental, yet too precise to be random. This exploration will challenge everything you thought you knew about the nature of existence itself. Think of a vast control panel with countless dials and switches, each representing a fundamental constant of nature. The gravitational constant determines how strongly matter attracts other matter. The strength of the electromagnetic force governs how atoms bind together. The cosmological constant sets the rate of the universe's expansion. Now imagine that every single one of these dials must be set to an almost impossibly precise value for stars to ignite, planets to form, and life to emerge. If the force holding atomic nuclei together were just a few % weaker, hydrogen would be the only element in existence, and the complex chemistry of life would be impossible. If it were slightly stronger, all the hydrogen in the early universe would have fused into heavier elements, leaving no water or fuel for stars. The gravitational constant presents another razor's edge. If gravity were stronger, stars would burn through their fuel at a ferocious rate, collapsing into black holes before life could develop on any orbiting worlds. A weaker gravitational constant would prevent stars from forming at all, leaving the universe a cold, dark soup of dilute gas. This isn't theoretical speculation. It's a mathematical reality that physicists began to fully appreciate in the 1970s. Cosmologist Martin Rees captured this astonishment perfectly when he described our universe as a biophilic one, a cosmos seemingly tailor-made for living creatures. The statistical improbability is beyond comprehension. The cosmological constant, which drives the acceleration of the universe's expansion, is fine-tuned to about 1 part in 10 to the 120th power. That's a 1 followed by 120 zeros, a number so vastly larger than the number of particles in the observable universe that it defies any ordinary notion of chance. Leonard Susskind, a father of string theory, refers to this as the cosmic landscape problem, noting that the value of this constant appears to be a selection from a nearly infinite array of possibilities, almost all of which would result in a dead, empty, or rapidly collapsing cosmos. This realization didn't emerge from philosophical musing but from the hard equations of 20th century physics. As we developed a deeper understanding of nuclear processes in stars, the formation of galaxies, and the initial conditions of the Big Bang, scientists were forced to confront a startling fact. The laws of physics as we know them are not just a set of arbitrary rules. They are a very specific, highly improbable recipe that allows for our existence. This presents us with the central mystery that has captivated physicists and philosophers alike. Are we the beneficiaries of the most spectacularly unlikely lottery win in all of existence, a 1 in a trillion chance? Or does the incredible precision of these cosmic dials point toward something more profound, a deeper principle or even a purpose behind the curtain of reality? Faced with this staggering improbability, we naturally search for explanations. One compelling approach sidesteps the need for a designer or cosmic accident altogether, suggesting instead that we're asking the question from the wrong perspective. This is the anthropic principle, first formally articulated by astrophysicist Brandon Carter in 1974 during a conference celebrating Copernicus. Ironically, while Copernicus moved us from the center of the universe, Carter's principle subtly recentered our importance by noting a simple but profound truth. We observe a universe compatible with our existence precisely because we exist to observe it. If the constants were different, we wouldn't be here to wonder about them. It's a cosmic version of survivorship bias. Imagine a puddle of water waking up one morning and thinking, "This is an astonishing world I find myself in. This hole in the ground fits me perfectly. It's exactly my shape with just the right depth and contours to hold every drop of me. It must have been made specifically for me." The puddle, of course, fails to recognize that it has simply adapted to fill the hole, not the other way around. In the same way, we might be the puddle marveling at a universe that seems perfectly tailored for life, when in reality, life has simply adapted to the universe's given parameters. This idea branches into two main interpretations. The weak anthropic principle is the less controversial version. It simply states that our location in the universe is necessarily privileged to the extent of being compatible with our existence as observers. We must find ourselves in a universe capable of sustaining life at a time when stars are shining and on a planet with the right conditions. It's a selection effect on a cosmic scale. The strong anthropic principle takes a much more provocative step. It suggests that the universe must have properties that allow life to develop within it at some stage in its history. This version hints at a deeper necessity, almost as if the laws of physics are compelled to permit observers. Philosopher Nick Bostrom has extensively explored these observer selection effects, framing them within his thinking about anthropic reasoning and probability. He might ask us to consider a thought experiment. Imagine a vast casino with countless slot machines, each representing a universe with different physical constants. Most machines are losers' universes that collapse instantly, or where matter never coalesces. But we, as observers, can only find ourselves standing in front of the one machine that hit the jackpot, the one universe that allowed us to be here. The question of why this machine is meaningless because we couldn't be anywhere else. While elegant, the anthropic principle faces a significant criticism. Many argue it doesn't truly explain the fine-tuning, it merely describes the situation, saying, "We observe fine-tuning because we exist," feels almost tautological. It tells us why we see what we see, but it doesn't address the deeper mystery of why this particular life-permitting universe exists at all. Why is there a winning slot machine in the casino? The principle is often seen as a philosophical placeholder, acknowledging a selection bias without providing a mechanism for why such a biased set of conditions came to be. It successfully prevents us from drawing premature conclusions about design, but it leaves us hungry for a more substantive answer about the origin of these exquisitely balanced rules. But if the anthropic principle feels like a philosophical shrug, a way to acknowledge the mystery without truly solving it, then perhaps we need a more expansive canvas on which to paint our explanation. What if our universe isn't the only one? What if the cosmic lottery wasn't a single miraculous draw, but an endless series of rolls where winning tickets, while rare, are statistically inevitable? This brings us to the multiverse hypothesis, a breathtakingly vast concept that suggests our finely tuned reality is just one bubble in an infinite cosmic foam, one page in a library containing every possible book of physical law. The foundation for this idea comes from a theory designed to solve other cosmic puzzles. In the early 1980s, physicist Alan Guth proposed the concept of cosmic inflation to explain why our universe is so remarkably uniform in all directions. He suggested that a fraction of a second after the Big Bang, space itself underwent a period of hyper-expansion, smoothing out the cosmos and seeding the structures we see today. But a fascinating implication of this theory, later developed by Andre Lind and others, is that this inflationary process might not be a one-time event. Instead, it could be eternal, a self-replicating process where the fabric of spacetime continually spawns new pocket universes in a never-ending chain reaction. In this eternal inflation scenario, each of these bubbles could crystallize with its own unique set of physical constants, like soap bubbles freezing with different patterns. The strength of forces, the number of dimensions, even the very nature of matter and energy could be randomly determined as each new universe inflates and cools. Our universe, with its perfect balance for life, would simply be one fortunate roll of the dice in a casino that never closes. This idea finds another compelling expression in string theory. To unify all fundamental forces, string theory requires extra spatial dimensions beyond the three we experience. But the mathematics suggests a staggering number of ways these dimensions could be compactified or folded in on themselves, perhaps 10 to the 500 different possible configurations. Each configuration would result in a universe with completely different physics. This is what physicists call the string theory landscape, a vast, abstract terrain of possibilities where each valley represents a stable universe with its own unique laws. In this landscape, finding a universe like ours isn't a miracle. It's a statistical certainty given enough possibilities. We are the inevitable winners in a cosmic game of chance, living in one of the few universes where the numbers came up right for complexity and consciousness. To make sense of this dizzying plurality, cosmologist Max Tegmark proposed a classification system for multiverses, organizing them into 4 distinct levels. Level 1 is simply our own observable universe extended infinitely far. In an infinite space, every possible configuration of matter will eventually repeat, meaning there are infinitely many identical copies of you reading this script right now. Level 2 introduces the bubble universes of eternal inflation, each with potentially different physical constants. Level 3 arises from the many worlds interpretation of quantum mechanics, where every quantum decision spawns a branching of reality into parallel timelines. Finally, level 4 is the ultimate multiverse, the set of all possible mathematical structures, a cosmos where every logically consistent set of physical laws actually exists somewhere. In this framework, our universe's fine-tuning loses its mystery. It's not fine-tuned at all. It's just one random outcome among an infinite array of others, most of which are barren and lifeless. We shouldn't be surprised to find ourselves in a habitable universe any more than a lottery winner should be surprised to hold the winning ticket. Someone had to win, and we are the someones. This is an elegant and powerful idea, but it comes with profound scientific and philosophical challenges. The most significant criticism is testability. If these other universes are permanently separated from us by inflationary expanses of space or different dimensional structures, how can we ever gather evidence that they exist? Critics argue that a theory that predicts everything ultimately explains nothing, and that the multiverse hypothesis risks veering into metaphysics rather than remaining within the bounds of empirical science. Furthermore, even if we accept an infinite multiverse, we face the measure problem. How do we calculate probabilities in an infinite ensemble? If there are infinitely many universes with life and infinitely many without, the concept of probability breaks down. We are left with the same profound question, simply transplanted to a larger stage. Why does this particular set of laws, out of all the possibilities, manifest as our experienced reality? The multiverse offers a compelling escape from the need for a designer, but it may also demand that we radically redefine what we consider a scientific explanation, pushing the boundaries of our understanding to the absolute limit. While the multiverse theory spreads our fine-tuning problem across an infinite cosmic landscape, another revolutionary idea suggests the answer isn't out there in space, but deep within time itself. What if universes don't just randomly spawn with fixed rules, but actually evolve? This is the breathtaking premise of physicist Lee Smolin's theory of cosmic natural selection, a proposal that applies Darwin's powerful principles of variation and selection to the cosmos itself. Imagine not a static multiverse, but a living, breathing cosmic ecosystem where universes reproduce, mutate, and compete for dominance. In this startling vision, black holes aren't the destructive endpoints we often imagine, but rather cosmic wombs, the birthing centers for new universes that inherit, with slight variations, the physical laws of their parents. The mechanism Smolin proposes is as elegant as it is radical. When a massive star collapses into a black hole, its immense gravity crushes matter to densities so extreme that our current laws of physics break down. At this singularity, space and time as we know them cease to exist. Smolin suggests that this catastrophic collapse might not be a final ending, but a transformation, a cosmic rebirth where the compressed singularity literally bounces outward into a new expanding universe. This daughter universe wouldn't be an identical copy of its parent. Just as biological reproduction involves random mutations in genetic code, this cosmic birthing process might introduce tiny, random variations in the fundamental constants of physics. The strength of gravity, the mass of electrons, the cosmological constant, all might shift slightly as a new universe is born from a black hole's collapse. This sets the stage for a truly cosmic form of evolution. Universes that by chance have physical constants conducive to producing many black holes would become reproductively successful. They would spawn more daughter universes which would inherit their fit characteristics. Over countless generations, the population of universes would evolve toward those parameters that maximize black hole production. Smolin uses the powerful analogy of a fitness landscape from evolutionary biology. Picture a vast, mountainous terrain where each location represents a different set of physical constants. The height of the terrain at each point represents how successful a universe with those constants would be at producing black holes. Through random mutations at birth, universes explore this landscape. Those that stumble into higher ground parameter combinations that generate more black holes have more offspring, gradually pulling the population of universes toward the peaks of black hole productivity. This creates a fascinating and somewhat humbling perspective on our own existence. If Smolin is correct, our universe isn't fine-tuned for life at all. It's fine-tuned for making black holes. The same constants that allow for galaxies, stars, planets, and ultimately life might simply be byproducts of this cosmic evolutionary process. Carbon-based life forms might be accidental tourists in a universe optimized for gravitational collapse. This insight turns the anthropic principle on its head. We don't live in a universe designed for us. We live in a universe designed for making black holes, and we just happen to be possible within that particular parameter set. The theory makes several testable predictions that distinguish it from multiverse hypotheses. Most significantly, it suggests that any change to the physical constants that would increase the number of black holes our universe produces should be impossible because we already exist at a peak of the fitness landscape. Smolin and others have explored whether tweaking parameters like the mass of the neutron or the strength of the strong nuclear force would increase black hole formation. The theory also predicts that the maximum mass of neutron stars, the dense remnants of dead stars that hover on the brink of becoming black holes, should be precisely tuned to allow the maximum number of stars to cross that threshold. Current astrophysical observations of neutron star masses provide some intriguing, though not conclusive, support for this prediction. However, cosmic natural selection faces significant challenges. The mechanism by which a black hole singularity transforms into a new expanding universe remains speculative, requiring physics beyond our current understanding. Critics question whether the theory truly explains fine-tuning or merely shifts the mystery to a different level. Why would the laws of physics allow this reproductive process in the first place? Why should black hole formation be the measure of fitness? Furthermore, the theory currently lacks direct observational evidence that would definitively confirm or refute it. While fascinating and intellectually compelling, it remains a provocative hypothesis rather than an established scientific explanation. Yet its power lies in offering a truly causal mechanism for fine-tuning, one that operates within time and across generations of universes, providing a narrative of cosmic evolution that is both scientifically grounded and profoundly imaginative. Yet another perspective pushes this mathematical foundation even further into the realm of the metaphysical. What if the universe isn't just described by math with uncanny accuracy, but what if it is math? This is the radical, almost psychedelic proposal at the heart of Max Tegmark's mathematical universe hypothesis. He suggests that our physical reality isn't merely modeled by mathematics, it is a mathematical structure. In this view, the universe isn't something that mathematics helps us understand. It is mathematics itself, an abstract structure that exists independently in a vast, timeless Platonic realm. This idea is so profound that it echoes a belief held by the ancient Greek philosopher Pythagoras over 2,000 years ago, who famously declared that all things are number. Tegmark's hypothesis dares to suggest that Pythagoras wasn't just being poetic. He might have been fundamentally, literally correct about the nature of reality. To grasp this, we need to consider what a mathematical structure actually is. Think of the rules of chess. The game exists as a set of abstract relationships and constraints, how the pieces move, how turns are taken, what constitutes checkmate. These rules are not physical, you can't touch them or see them, Yet any physical manifestation of chess, a wooden board, a digital simulation, or even two people playing in the sand with sticks, is just an imperfect representation of that perfect, underlying abstract structure. Tegmark proposes that our universe operates on the same principle. The particles, forces, and spacetime we experience are not the fundamental reality. They are merely the physical manifestation of a deeper, immutable mathematical structure. The laws of physics aren't laws that the universe follows. They are the identity of the universe itself, the defining properties of this particular mathematical object. This perspective offers a breathtakingly elegant solution to the fine-tuning problem. If the universe is a mathematical structure, then its properties aren't chosen or tuned at all. They are simply necessary truths, inherent and inseparable from the structure itself, just as the sum of angles in a Euclidean triangle is always 180 degrees. There is no why behind the value of the gravitational constant or the charge of an electron. Asking why these constants have the values they do is like asking why the number 4 follows the number 3. They are simply baked into the logical structure of the mathematical entity that we call our universe. The reason mathematics is so unreasonably effective at describing physics is therefore no longer a mystery. It's not that physics is mathematical, it's that physics is mathematics. We are not discovering the laws of the universe, we are discovering the properties of the mathematical structure we are embedded within. Tegmark himself frames this with a compelling clarity, stating that our universe isn't just described by math, but that it is math in a very specific sense. He invites us to consider ourselves as self-aware patterns within a giant mathematical object. This is a form of extreme mathematical Platonism, the belief that mathematical entities exist in a real, objective realm outside of space and time. Other thinkers, like Roger Penrose, have also expressed sympathy for this view, suggesting that the mathematical world has its own independent existence and our physical world is a shadow of it. This idea dissolves the boundary between the abstract and the concrete, proposing that mathematical existence and physical existence are one and the same. If a structure is mathematically consistent, then it exists in every sense that matters. The implications are staggering. It suggests that every possible mathematically consistent universe actually exists. Our cosmos is just one particular structure in a vast multiverse of mathematical realities, some simple and some incredibly complex. This is Tegmark's Level 4 multiverse, the ultimate ensemble of all possible structures. In this framework, the mystery of our universe's life-permitting rules completely vanishes. We don't inhabit a special or finely tuned universe. We simply inhabit one that is mathematically possible and complex enough to contain self-aware substructures like us that can observe and ponder their own existence. The hypothesis doesn't so much solve the fine-tuning problem as it completely reframes and dissolves it, replacing a physical mystery with a mathematical inevitability. But what if the answer to our cosmic fine-tuning mystery isn't found in vast multiverses or evolving cosmos, but in something far more familiar to our modern technological age? What if our universe's exquisitely balanced rules weren't chosen by nature at all, but programmed by some form of advanced intelligence? This startling possibility forms the core of Nick Bostrom's simulation hypothesis, a provocative argument that bridges cosmology, computer science, and philosophy with breathtaking implications. Bostrom, a philosopher at the University of Oxford, presents us with a compelling trilemma, 3 possibilities, one of which he argues must almost certainly be true. Either advanced civilizations inevitably go extinct before developing the capability to create realistic simulations, or they choose not to run such simulations for ethical or practical reasons, or we are almost certainly living in a simulation right now. The logic behind this argument rests on some reasonable assumptions about technological progression. If civilizations can avoid self-destruction and continue advancing technologically for thousands or millions of years, they would eventually develop computing power so vast that simulating entire universes, complete with conscious beings, would become possible. Once this capability exists, the number of simulated minds could quickly dwarf the number of biological minds in the base reality. From a statistical standpoint, the odds would overwhelmingly favor any given conscious experience being a simulated one rather than a biological original. Think of it like this. Imagine a future civilization that enjoys creating historical simulations as a form of entertainment or research. They might create billions of simulations of 21st century Earth, each with billions of digitally conscious beings who believe they're living in the real world. Now consider the total population of that original civilization, perhaps billions or trillions of biological beings. The simulated minds would outnumber the original minds by an almost infinite ratio. If you were a conscious being experiencing what seems like 21st century life, the statistics suggest you're far more likely to be one of the simulations than one of the rare originals. This creates the haunting possibility that we might be living in what philosophers call a nested simulation, a simulation within a simulation, perhaps many layers removed from whatever constitutes base reality. Our universe's apparent fine-tuning could then be explained not as a cosmic accident or metaphysical necessity, but as a design choice. The physical constants might be set to their specific values because those values create an interesting, stable universe that can support complex structures and conscious life, the kind of universe that would be worth simulating. Alternatively, these values might represent computational optimizations. Perhaps certain physical parameters make the simulation more efficient to run, requiring less processing power or memory allocation. The fact that our universe appears quantized at the smallest scales with discrete packets of energy, quantized space, and fundamental particles fits remarkably well with the idea of a digital simulation running on some cosmic computer. This hypothesis gains additional plausibility when we consider the strange quantum mechanical properties of our universe. The wave function collapse upon observation, where particles seem to exist in multiple states until measured, could be interpreted as a rendering optimization, a way for the simulation to conserve processing power by only calculating definite properties when they're being observed. The speed of light as an ultimate speed limit might represent the maximum processing speed of the system running our reality. Even the apparent fine-tuning of the cosmological constant, which keeps the universe expanding at just the right rate to allow galaxy formation without immediate recollapse, could be seen as a stability parameter carefully chosen by the programmers to ensure a long-running, interesting simulation rather than a quick cosmic burnout. Of course, this mind-bending hypothesis faces significant challenges and criticisms. The computational requirements for simulating an entire universe down to the quantum level are truly astronomical, far beyond anything we can currently conceive. However, we might not need a full quantum-level simulation to create convincing conscious experiences. The programmers could be using sophisticated rendering techniques, only simulating details when they're being observed, much like video games render detailed environments only within the player's field of view. This concept, sometimes called the foveated rendering hypothesis, suggests our reality might contain far less resolution than we assume in places nobody is looking. More fundamentally, the simulation argument potentially leads to infinite regress. If we're in a simulation created by advanced beings who created them, are they also simulated by even more advanced beings? This chain of simulations might extend infinitely backward, leaving us with the same fundamental mystery of original creation, just transplanted to a different context. Despite these challenges, Bostrom's simulation hypothesis remains a fascinating and surprisingly robust framework for considering the nature of our reality. It connects ancient philosophical questions about the nature of existence with cutting-edge concepts in computer science and physics, creating a bridge between disciplines that rarely communicate. Whether we ultimately accept or reject the idea, it serves as a powerful reminder that our understanding of reality is still in its infancy, and that the truth about our universe might be far stranger than we've ever dared to imagine. The idea that our universe might reflect intentional design rather than blind chance is one of humanity's oldest and most persistent intuitions. Long before modern cosmology revealed the razor's-edge precision of physical constants, philosophers and theologians were already arguing that the astonishing order and complexity of the world pointed toward a cosmic purpose or designer. This line of reasoning is known as teleology, from the Greek word telos, meaning end or purpose. And while it might seem like an ancient relic in our age of quantum mechanics and multiverse theories, fine-tuning has given teleological arguments a powerful and sophisticated resurgence within scientific and philosophical circles. We can trace this intellectual thread back to the classical world. Plato, in his dialogue Timaeus, introduced the concept of a demiurge, a divine craftsman who shaped the chaotic, pre-existing materials of the cosmos into an orderly reality according to a rational and eternal blueprint. For Plato, the beauty, intelligibility, and mathematical harmony of the world were not accidents. They were evidence of a benevolent intelligence imposing form on matter. Centuries later, this idea found a famous expression in the natural theology of William Paley. In the early 19th century, Paley proposed his seminal watchmaker analogy. If you were walking across a heath and stumbled upon a stone, you might plausibly think it had lain there forever. But if you found a watch with its intricate gears and springs all perfectly arranged to tell time, you would immediately infer it had a maker. Paley argued that the natural world, from the exquisite complexity of the human eye to the precise orbit of planets, displays an even more profound level of intricate design, pointing inevitably to a divine intelligence. For a long time, many considered this argument fatally wounded by Darwin's theory of natural selection, which provided a powerful, non-teleological mechanism for the apparent design in biological systems. But the discovery of cosmic fine-tuning has moved the goalposts entirely. The issue is no longer the complexity of biological life, but the very laws and constants that make any complexity possible at all. Natural selection can explain the evolution of the eye once the universe exists with stable atoms, gravity, and chemistry, but it cannot explain why the universe has precisely the right parameters to allow atoms, chemistry, and long-lived stars in the first place. This has led contemporary philosophers and scientists to formulate a new, more robust version of the design argument, grounded in the mathematics of probability and the findings of modern physics. A leading proponent of this view is philosopher Robin Collins. He frames the fine-tuning not as absolute proof, but as a powerful inference to the best explanation using Bayesian probability, a formal way of updating the likelihood of a hypothesis based on new evidence. Collins argues that the existence of a life-permitting universe is enormously more probable under the hypothesis of a cosmic designer than under the hypothesis of a single, random, physical universe. The evidence of fine-tuning, he suggests, should significantly increase our confidence that some form of intentionality lies behind the cosmos. This isn't about inserting a God of the gaps to explain what science hasn't yet figured out. Instead, it's about interpreting the entire scientific framework itself, the shocking specificity of its foundational rules, as evidence that points beyond a purely materialistic explanation. Of course, this perspective faces significant and powerful criticisms from the scientific community. The most common objection is often called the God of the Gaps concern, the fear that invoking a designer is a lazy argument that halts scientific inquiry, plugging a mystery with a bigger mystery. If we say God did it to explain fine-tuning, critics ask, then who designed God? This leads to an infinite regress that arguably explains nothing. Furthermore, modern alternatives like the multiverse hypothesis provide a purely physicalist framework for explaining fine-tuning through sheer statistical volume, making a designer seem superfluous. If an infinite number of universes exist with all possible constants, then a life-permitting one is inevitable, and no designer is required. This naturalistic explanation, while currently untestable, remains for many a more parsimonious solution than positing a transcendent intelligence. Yet proponents counter that the multiverse theory itself requires its own set of unexplained, fine-tuned assumptions. What is the mechanism that generates these many universes? The inflationary field driving eternal inflation must itself be governed by laws and constants set to very specific values to produce any universes at all. This simply pushes the fine-tuning problem back one step, from the constants within universes to the meta-laws that govern the multiverse-generating mechanism. Some argue that this makes the designer hypothesis, which posits a single, ultimate reason for the laws of nature, actually the more elegant and economical solution. This ongoing debate reveals a deep and fascinating tension at the frontier of knowledge, where scientific discovery brushes up against metaphysical questions that have persisted for millennia. It challenges us to consider whether purpose might be a fundamental feature of reality, woven into the very fabric of the cosmos, waiting to be discovered not in the details of biology but in the immutable laws of physics themselves. But what if the fundamental stuff of reality isn't inert matter or energy, but something far more mysterious and intimate? What if consciousness itself is not a late-arriving product of complex biological computation, but a basic, intrinsic feature of the cosmos, present in some form at the very foundation of existence? This is the startling and ancient proposition of panpsychism, the idea that mind is a universal and fundamental property of matter. From this perspective, the universe's exquisitely balanced laws might not emerge from blind physical processes, but from something resembling a deep, proto-conscious inclination toward order and complexity. It suggests that the cosmos is not a vast, empty machine, but is in some sense awake, with experience being as basic to its nature as mass or electrical charge. The modern champion of this view is philosopher David Chalmers, who famously framed the hard problem of consciousness. The hard problem asks why and how physical processes in the brain give rise to subjective experience. The raw feeling of redness in a rose, the sharp taste of lemon, the profound ache of sadness. Physics can describe the neural correlates of these experiences in perfect detail, mapping the firing of neurons and the flow of neurotransmitters, but it seems to leave out the experience itself. Chalmers argues that it's possible to imagine a perfect physical duplicate of a human being, a philosophical zombie that behaves exactly like us but has no inner life whatsoever. The fact that we are not zombies, that we have rich inner experiences, suggests that consciousness is a fundamental feature that must be added to the list of the world's basic ingredients, alongside space, time, and mass. For Chalmers, panpsychism offers the most promising avenue for integrating consciousness into our scientific world, without resorting to magic or mysticism. If consciousness is fundamental, then it didn't suddenly emerge from non-conscious matter. It was always there, a basic property that simply becomes more complex and organized as matter itself becomes more complex. Another powerful voice for this perspective is philosopher Galen Strawson, a staunch physicalist who argues that panpsychism is actually the most logical conclusion of a truly consistent materialist view. He points out that we know consciousness exists as a real, concrete phenomenon. We also know it is intimately tied to the brain, a physical system. Therefore, he reasons, consciousness must itself be a physical property. It cannot come from nothing, and it cannot magically emerge from things that are utterly devoid of any experiential properties. This is the core of the argument against emergence. We accept that properties like fluidity emerge from the collective behavior of water molecules because we can clearly see how the molecular interactions produce the larger scale effect. But how could the firing of non-conscious neurons, no matter how complex their arrangement, ever generate a subjective feeling? The gap seems unbridgeable. Strawson concludes that the only coherent option is that some form of proto-consciousness, or experientiality, must be a fundamental property of the basic constituents of reality, perhaps even at the level of elementary particles. The electron may not be thinking, but it might possess some vanishingly simple form of experience, a bare whisper of feeling that forms the building block for the rich symphony of human consciousness. To grasp this, consider a powerful metaphor. Think of the fundamental properties of physics like mass and charge. We don't ask how an electron generates its negative charge. We accept that charge is just a basic, irreducible property that the particle simply has. Panpsychism suggests we should think of consciousness in the same way. It's not something that is produced. It is a fundamental aspect of certain physical structures, just as charge is. When these basic particles come together in the staggering complexity of a human brain, this fundamental property of consciousness doesn't vanish. It combines and integrates, giving rise to the rich, unified stream of awareness that you are experiencing right now. This view elegantly sidesteps the hard problem. Consciousness doesn't mysteriously emerge from non-conscious stuff. It was present all along, and complex consciousness simply emerges from the complex organization of already conscious entities. This perspective offers a fascinating new lens through which to view the mystery of cosmic fine-tuning. If some form of mind is indeed fundamental to reality, then the laws of physics might not be arbitrary rules, but could reflect a deep inclination toward the kinds of structures that can support and amplify conscious experience. The universe's constants could be set to values that encourage the formation of complex systems, galaxies, stars, planets, life, not as a random accident, but because complexity is a pathway for fundamental consciousness to express itself in richer and more profound ways. In this view, we are not accidental spectators in a meaningless cosmos. We are the universe becoming conscious of itself, local manifestations of a fundamental property that has been present since the first moment of the Big Bang. This creates a compelling bridge between the two traditional and opposing views of reality: hard materialism, which sees only matter in motion, and traditional dualism, which sees mind and matter as separate substances. Panpsychism offers a middle path, a form of realistic monism that says reality is composed of one kind of stuff, physical stuff, but that this stuff has an intrinsic inner, experiential aspect as well as its outer, observable properties. It's a vision of the cosmos that is both rigorously physical and deeply mindful, opening the door to possibilities that are far more strange and wonderful than anything we have yet dared to imagine. This profound mystery of time's arrow brings us to one of the most fundamental and yet puzzling features of our reality: the undeniable feeling that time moves forward, not backward. We remember the past, we anticipate the future, and we watch as milk mixes into coffee but never spontaneously unmixes. This seems so obvious, so ingrained in our experience, that we rarely pause to consider how bizarre it truly is. Because when we look at the fundamental laws of physics, from Newton's mechanics to Einstein's relativity to quantum electrodynamics, almost all of them are completely time-symmetric. The equations work just as well whether time flows forward or backward. There is nothing in the law of gravity that says an apple must fall down from the tree. The math would perfectly allow for an apple to suddenly leap up from the ground and reattach itself to a branch. The laws don't dictate a direction, they are indifferent to the flow of time. So why does our experienced reality have such a powerful one-way arrow? The key to this puzzle, physicists believe, lies not in the laws of motion themselves, but in a more subtle and powerful concept, entropy. Entropy is essentially a measure of disorder, of the number of ways a system's components can be rearranged without changing its overall appearance. A shattered glass on the floor has high entropy. The pieces can be in countless different positions, and it still looks like a mess. A fully assembled, intact glass on a table has very low entropy. There's essentially only one way for all the molecules to be arranged to form that specific glass. The second law of thermodynamics states that the total entropy of an isolated system always increases over time, or at best remains constant. It never decreases. This is the scientific foundation for time's arrow. Things tend to move from states of low probability and high order to states of high probability and disorder. It's why your tidy room will inevitably become messy if you don't exert effort to clean it, and why it's infinitely easier to scramble an egg than to unscramble one. The brilliant physicist Ludwig Boltzmann provided a stunning statistical explanation for this law in the late 19th century. He realized that high-entropy states are overwhelmingly more probable than low-entropy states simply because there are vastly more ways to be disordered than to be ordered. If you toss a deck of cards in the air, the chance they will land in a perfectly ordered sequence by suit and number is astronomically small. It's far more likely they'll land in a random, high-entropy mess. So the reason we see entropy increase is not because of a fundamental law forcing it, but purely because the universe is moving from a less probable state to a more probable one. The past is a state of incredibly low entropy, and the future is a state of high entropy, and we are living in the brief, wondrous window in between where the increase in disorder creates the energy flows and structures that make life and consciousness possible. This explanation, however, simply pushes the mystery back one step. It doesn't explain why the past had such a low entropy to begin with. Why was the early universe in such an incredibly ordered, low-entropy state? This is perhaps the deepest and most profound question in all of cosmology. The initial conditions of the Big Bang appear to be yet another example of cosmic fine-tuning. For entropy to increase and create the arrow of time we experience, the universe had to start in an exquisitely special, low-entropy configuration. Nobel laureate Roger Penrose has calculated just how special this initial state was. He estimates that the probability of the universe starting with such low entropy is about 1 part in 10 to the power of 10 to the 123, a number so unimaginably large that it makes the fine-tuning of the cosmological constant seem trivial by comparison. This isn't just a winning lottery ticket. This is a lottery where every single atom in the observable universe has to independently win the jackpot over and over again. Penrose himself has proposed a fascinating, if speculative, solution to this enigma called the Weyl curvature hypothesis. In Einstein's theory of general relativity, the curvature of spacetime is described by a complex mathematical object. Part of it relates to the mass and energy present, which is what causes gravity. Another part, called the Weyl curvature, describes the tidal forces that can tear structures apart, like those near a black hole singularity. Penrose suggests that at the initial singularity of the Big Bang, the Weyl curvature was constrained to be zero or very nearly zero. This means the universe began in an incredibly smooth and uniform state, a state of very low gravitational entropy. As the universe expanded and evolved, the Weyl curvature was free to increase, allowing for the formation of galaxies, stars, and black holes, all of which represent a huge increase in gravitational disorder and thus drive the arrow of time forward. In this view, the ultimate reason time flows forward is because of a very specific and still unexplained constraint on the geometry of the universe at its birth. This deep connection between memory and entropy is perhaps the most personal and profound illustration of time's arrow. Your ability to remember the past but not the future is not a quirk of your biology. It is a direct consequence of the second law of thermodynamics. Forming a memory is a physical process in your brain that involves a particular configuration of neurons and a specific chemical state. This process, like any other, increases the total entropy of the universe. It creates a record, but it also dissipates energy and increases disorder. You can remember the past because it is a state of lower entropy. You cannot remember the future because it is a state of higher entropy. There is no physical record of it yet to be accessed. Your very consciousness, your sense of a narrative flowing from yesterday to tomorrow, is inextricably linked to this grand, cosmic progression from order to disorder. The unwritten rule of time's arrow is therefore not just a feature of the cosmos. It is the very substrate of experience, the fundamental condition that allows for history, causality, and the unfolding of story itself. Now, if the arrow of time emerges from a specific, finely tuned initial condition of low entropy, that is one thing. But what if the very fabric of reality at its smallest scales operates on a completely different set of principles, where certainty is replaced by probability, and the very act of looking changes what is seen? This brings us to the bizarre and beautiful world of quantum mechanics, a domain where the universe's rulebook seems to have been written in a language of pure potentiality. At the heart of this quantum realm lies a fundamental fuzziness, a core of probability that challenges our most basic intuitions about how reality should work. The perfect gateway into this strangeness is the famous double-slit experiment, a deceptively simple setup that reveals one of physics' deepest mysteries. Imagine a barrier with two thin, parallel slits cut into it. Behind this barrier is a screen that lights up when particles hit it. Now, if you fire a stream of tiny particles like electrons at this barrier, you would logically expect to see two bright bands on the screen directly behind the two slits, as the particles are blocked everywhere else. And that is exactly what happens when you treat the electrons as little bullets, but the magic and the mystery unfolds when you start to think of these electrons not as particles but as waves. If you perform the experiment with waves of water or sound, you get an interference pattern. The waves pass through both slits, ripple outward, and then overlap. Where a peak from one wave meets a trough from another, they cancel each other out, creating a dark band. Where peak meets peak, they reinforce each other, creating a bright band. The result on the screen is not two bands, but a whole series of light and dark stripes called an interference pattern. Now, here is the utterly astonishing part. When you fire electrons one at a time at the double-slit barrier, they each arrive at the screen as a single, localized dot, like a tiny particle. But as you continue this process, sending thousands of electrons through one by one, that series of individual dots slowly builds up to form an interference pattern. It is as if each individual electron is somehow going through both slits at once, interfering with itself, and then deciding where to land on the screen. This is the essence of wave-particle duality. The electron is not a particle or a wave. It behaves as both, or rather, it exists in a ghostly state of potentiality that only crystallizes into a definite location upon measurement. This leads us directly to the concept of superposition, the idea that a quantum system doesn't exist in a single, definite state, but in a blurred combination of all possible states simultaneously. It is only when we measure it, when we look at it, that this probability cloud collapses into one specific outcome. This was the central point of Erwin Schrödinger's famous and somewhat morbid thought experiment. He imagined placing a cat in a sealed box with a radioactive atom, a Geiger counter, a hammer, and a vial of poison. If the radioactive atom decays, the Geiger counter triggers the hammer to break the vial, killing the cat. According to the quantum rules of superposition, until someone opens the box and looks inside, the radioactive atom is in a superposition of both decayed and not decayed. And therefore, by extension, the poor cat must also be in a superposition of both alive and dead. A bizarre and unsettling proposition that Schrödinger devised precisely to highlight what he saw as the absurdity of applying quantum weirdness to the everyday world. This act of measurement, the moment a probability becomes a certainty, is known as the measurement problem, and it remains one of the greatest unsolved puzzles in physics. Why should the act of observation have any effect on reality? What exactly constitutes a measurement? Is it a conscious observer or simply an interaction with a larger system? The founding fathers of quantum mechanics, gathered in Copenhagen around Niels Bohr, proposed a pragmatic solution that became the standard interpretation. The Copenhagen interpretation essentially says that it is meaningless to talk about what a particle is really doing before we measure it. The particle does not have a definite position or momentum. It only has a set of probabilities described by its wave function. The act of measurement forces the wave function to collapse, picking one possibility from the menu. As Bohr himself famously argued, we must abandon the classical idea of a reality independent of measurement. It is wrong to think that the task of physics is to find out how nature is, he said. Physics concerns what we can say about nature. This deeply unsettled other giants, most notably Albert Einstein, who found the idea of a universe governed by chance and observer-dependent reality profoundly unsatisfying. He believed in an objective reality that existed whether anyone was looking or not, famously arguing that God does not play dice with the universe. As a challenge to the Copenhagen view, Einstein, along with Boris Podolsky and Nathan Rosen, devised a thought experiment that they believed exposed a flaw in quantum theory. This EPR paradox, as it became known, involved a pair of particles that interact and become linked or entangled. According to quantum mechanics, you could separate these two particles by any distance across a room or across the galaxy, and they would remain mysteriously connected. Measuring a property of one particle, say its spin, would instantly determine the spin of its partner, seemingly violating the cosmic speed limit set by the speed of light. Einstein derided this spooky action at a distance as evidence that quantum mechanics must be an incomplete theory, that there must be some hidden variables, some deeper layer of reality that determines the properties of particles from the moment they are created. For decades, this was a philosophical debate. Then, in the 1960s, physicist John Bell devised a mathematical theorem that could actually test whether these hidden variables could exist. Experiments conducted since then have consistently confirmed the predictions of quantum mechanics. Entanglement is real. Measuring one particle does instantly influence its partner, confirming that reality at a fundamental level is non-local. This doesn't allow for faster-than-light communication, but it does show that the universe is far more interconnected than our classical intuition would ever allow. The profound unease with the Copenhagen interpretation's reliance on measurement and collapse has led to other compelling interpretations. Perhaps the most audacious is the many worlds interpretation proposed by Hugh Everett III. Everett took the mathematics of the wave function at face value and suggested that it never actually collapses. Instead, at the moment a measurement seems to force a choice, the cat is alive or dead, the entire universe splits into multiple branches. In one branch, an observer finds a live cat. In another, a different version of that same observer finds a dead cat. Both outcomes are equally real, but they play out in parallel, non-communicating universes. In this view, the randomness we perceive is just an illusion. Every possible outcome of every quantum event actually occurs, but we only experience one branch of the ever-branching tree of reality. It is a breathtakingly vast and strange picture, but one that elegantly eliminates the need for a special measurement process or wave function collapse. These competing interpretations, from Copenhagen's pragmatic observer dependence to many worlds' dizzying multiplicity, highlight the core mystery. Do the probabilistic rules of quantum mechanics represent the final, fundamental truth about reality, or are they merely a description of our ignorance, a set of rules for navigating a deeper, hidden reality that we have not yet discovered? This question goes straight to the heart of our theme. The quantum rules were not written in a classical language of certainty and determinism. They appear to have been written in a language of probability and potential, a set of instructions for a game where the dice are loaded not by chance, but by a logic we are still struggling to comprehend. But if the bizarre rules of quantum mechanics challenge our understanding of particles and probability, an even more revolutionary idea is now shaking the very foundations of reality itself. What if the stage upon which this quantum drama plays out, space and time, isn't fundamental at all? For centuries, we've assumed that space is the eternal, unchanging container of the universe and time is the uniform river in which all events unfold. But a growing body of theoretical physics suggests this might be a profound illusion. Space and time themselves might not be primary ingredients of reality, but instead emergent properties that arise from something deeper, more abstract, and utterly foreign to our everyday experience. This radical concept begins with a simple but powerful shift in perspective. Instead of thinking of the universe as a collection of objects existing in space and time, we might need to think of it as a vast network of relationships. Imagine reality not as a cosmic stage with actors moving about, but as the intricate web of connections between the actors themselves. The stage space and time might simply be a useful construct that emerges from the patterns of their interactions. This isn't just philosophical speculation. It's a direction of research being pursued by some of the world's leading physicists, and it finds one of its most compelling expressions in the holographic principle. First proposed by Gerard T. Hooft and later developed by Leonard Susskind, the holographic principle draws a stunning analogy from an everyday security hologram. On a credit card, a two-dimensional plastic film encodes all the information needed to project a three-dimensional image. The principle suggests that our three-dimensional universe, with all its rich content of stars, planets, and people, might itself be a projection from a two-dimensional surface at its boundary. All the information that describes everything happening within a volume of space could be encoded on its outer surface, like a cosmic version of a hologram. The physicist Juan Maldacena provided a concrete mathematical realization of this idea with his discovery of anti-de Sitter/conformal field theory correspondence, or AD-S/CFT. This is a powerful duality which shows that a gravitational theory in a hypothetical bulk universe with 5 dimensions is completely equivalent to a quantum field theory without gravity living on its 4-dimensional boundary. In this holographic duality, the physics inside the volume is exactly mirrored by the physics on its surface. This suggests that our visceral experience of living in a 3-dimensional world might be a projection, and that the true, fundamental degrees of freedom of the universe are living on a distant, lower-dimensional surface. This idea finds another powerful voice in the work of Eric Verland, who has proposed a theory of emergent gravity. Verland starts with the concept of entropy, which we typically associate with disorder and information. He suggests that gravity might not be a fundamental force at all, but an emergent phenomenon, much like the pressure of a gas, is not a fundamental property of air, but emerges from the collective statistical behavior of countless molecules colliding. In Verland's view, the fabric of spacetime itself emerges from the quantum information associated with the fundamental building blocks of reality. When space is empty, this information is in a state of equilibrium. But when matter is present, it disturbs this equilibrium, and gravity emerges as an entropic force, a tendency for the system to return to a state of maximum entropy. This is a breathtaking inversion of our usual thinking. Newton and Einstein gave us laws of gravity. Verland is suggesting that gravity itself is a consequence, a side effect of something more primary, information, and the way it is processed and stored at the most fundamental level. To make this abstract idea tangible, consider the emergence of temperature. When you touch a hot stove, you feel heat, but what is heat fundamentally? At the microscopic level, there is no such thing as temperature. There are only molecules vibrating with different amounts of kinetic energy. Temperature is a collective, statistical property that emerges from the average motion of trillions upon trillions of molecules. It has no meaning for a single atom. In a very similar way, physicists like Verland are arguing that space and time might be emergent concepts. The smooth, continuous spacetime we perceive might be a macroscopic approximation, a useful illusion that emerges from the collective behavior of countless fundamental, non-spatial entities. Imagine looking at a digital photograph on a screen. From a distance, you see a smooth, continuous image with shapes, shadows, and depth. But if you zoom in far enough, you see that the image is actually composed of discrete pixels. The illusion of continuity emerges from the dense packing of these individual points. Our universe might operate on a similar principle. The continuous fabric of spacetime might be woven from discrete, fundamental atoms of space and time, often theorized to exist at the minuscule Planck scale. Perhaps the most profound thread connecting these ideas is the increasingly clear link between spacetime and quantum entanglement. Entanglement, that spooky action at a distance that so troubled Einstein, appears to be the glue that literally holds space together. Research by physicists like Mark van Romsdonk has shown that if you take a quantum system and gradually reduce the amount of entanglement between its different parts, the geometric connectivity between those parts begins to degrade. In the extreme case, if you eliminate all entanglement, the space itself seems to tear apart. This suggests that the very geometry of space, the fact that 2 points are close together and connected, is a manifestation of how entangled the quantum information at those points is. The more entangled 2 regions are, the closer they are in spacetime. This turns our classical intuition inside out. We normally think that 2 particles can become entangled because they are close together and interact. This new view suggests they are close together because they are entangled. The geometry of the universe might be built from these quantum connections. This revolutionary perspective forces us to confront a possibility that is as exciting as it is disorienting. The ultimate theory of reality might not be written in the language of geometry, of curves in space-time and gravitational fields. It might be written in the language of information, of bits and entanglement and quantum computation, the familiar stage of space and time upon which we have always believed the cosmic drama unfolds, might itself be part of the show, a magnificent illusion emerging from a deeper, more abstract reality that operates by a completely different set of rules. We are like characters in a video game who have just begun to suspect that the world we inhabit is rendered from code, and that the true reality exists in the circuitry of the computer. This doesn't make our experience any less real, but it fundamentally changes our understanding of what real actually means, pointing toward a cosmos that is far more strange, interconnected, and intellectually thrilling than we ever imagined. Now consider the most famous mathematical constant of all, pi. This number, representing the ratio of a circle's circumference to its diameter, has been known for millennia. The ancient Babylonians and Egyptians had rough approximations, and Archimedes famously used polygons to narrow it down to between 3 1/7 and 3 10^71. It appears in the most fundamental equations describing our universe, from Einstein's field equations for general relativity to Heisenberg's uncertainty principle in quantum mechanics. It's nestled in Coulomb's law for the force between two electric charges and is essential for calculating the period of a pendulum. Pi seems to be woven into the very geometry of spacetime itself. But why should a constant derived from circles be so ubiquitous in laws that govern everything from the orbit of planets to the behavior of light? Then there's Euler's number, E, approximately 2.71828. Unlike pi's geometric origin, E emerges from the mathematics of growth and decay. It is the base rate of growth shared by all continually growing processes. It appears when we calculate compound interest that is continuously compounded, and it is the unique number where the derivative of the exponential function e to the x is itself. This profound property makes it indispensable in calculus, and therefore, in the differential equations that form the backbone of physical law. You find E describing radioactive decay, population growth in biology, and the cooling of a hot object. It is central to the normal distribution in statistics, which describes everything from measurement errors to the distribution of heights in a population. The Schrödinger equation, the very heart of quantum mechanics, is built upon E raised to an imaginary power, connecting it intimately with pi through Euler's formula. This constant seems to govern the rhythm of change throughout the natural world. Beyond these two giants, we encounter a host of other mysterious numbers. The golden ratio, approximately 1.618, appears in the spiral arrangements of sunflower seeds, the branching of trees, and the proportions of the Parthenon. The fine structure constant, approximately 1/137th, dictates the strength of the electromagnetic interaction between elementary particles. Each of these constants is a pure, dimensionless number. They are not measured in meters or seconds. They are fundamental ratios that seem to be hard-coded into the operating system of reality. The question that has haunted physicists and mathematicians for centuries is whether these values are necessary or contingent. Are they the only possible values that could work, forced upon the universe by the ironclad logic of mathematics? Or are they arbitrary, like the settings on a vast cosmic control panel, which just happen to be set this way in our particular universe? This touches on what Nobel laureate Eugene Wigner famously called the unreasonable effectiveness of mathematics in the natural sciences. Why should human-invented mathematical concepts, some derived from purely abstract games of the mind, provide such a powerful and precise language for describing the physical world. It is as if we discovered a key that perfectly fits a lock we knew nothing about. The physicist Max Tegmark, with his mathematical universe hypothesis, takes this idea to its ultimate conclusion. He argues that this effectiveness is no coincidence because the universe is mathematics. In this view, pi isn't just a number that describes circles in our universe. It is an intrinsic property of the particular mathematical structure that is our universe. Its value isn't chosen. It is a necessary and inevitable feature of that structure, just as the number of sides on a square is necessarily 4. Yet, an alternative perspective suggests these constants might be contingent. They could have been different. In the vast landscape of possible universes implied by string theory, different regions of the cosmos or different bubble universes could have different values for these fundamental numbers. In most of those universes, the values would not permit the formation of complex structures like atoms, stars, or life. We find ourselves in a universe with this particular set of constants for the same reason we find ourselves on a planet with breathable air and liquid water, because we couldn't exist otherwise. This anthropic reasoning offers an explanation, but to some, it feels like a retreat from a deeper truth. It explains why we observe these values, but doesn't explain why these particular mathematical relationships hold such privileged sway over the behavior of matter and energy. The mystery persists not as a problem to be solved, but as a profound feature of our existence, a silent, mathematical harmony underlying the apparent chaos of the physical world, waiting to be discovered but perhaps never fully explained. This elegant connection between symmetry and conservation is perhaps the most beautiful and profound discovery in all of theoretical physics, and it came not from a laboratory experiment, but from the mind of a mathematician named Emmy Noether. Working in relative obscurity in 1918, Noether proved a theorem of such breathtaking power and generality that it forever changed our understanding of the universe's rulebook. Her insight was deceptively simple. For every continuous symmetry in the laws of physics, there corresponds a conservation law. A continuous symmetry is one where you can make a tiny, smooth change to a system, and its fundamental behavior remains identical. Rotate a laboratory experiment by a few degrees, or shift it across the room, or run the experiment tomorrow instead of today. If the underlying physics is the same, if the outcome doesn't depend on your choice of orientation, location, or moment in time, then that symmetry guarantees something is conserved. The symmetry of rotation, the fact that the laws of physics don't have a preferred direction, leads directly to the conservation of angular momentum. The symmetry of spatial translation, the idea that an experiment works the same here as it does there, implies the conservation of linear momentum, and most profoundly, the symmetry of time translation, the fact that the fundamental rules don't change from one moment to the next, demands the conservation of energy. Noether's theorem is the hidden engine beneath the most fundamental pillars of reality. It tells us that the steadfast reliability of these conservation laws isn't an accident. It is the direct mathematical consequence of the fact that the universe plays by the same rules everywhere and everyone. This profound mathematical beauty extends far beyond the symmetries we can see and feel, reaching into the most abstract and powerful principles governing the forces of nature. This is the realm of gauge symmetry, a concept that sounds esoteric but is actually the master key to understanding how particles interact. At its heart, a gauge symmetry is a kind of mathematical redundancy, a freedom to change how we describe a system in a certain way without changing any of its observable physical predictions. It's like being able to change the color palette on a map. The names of the colors are arbitrary and can be changed at will, but the underlying borders and topography, the actual physical information, remains untouched. In physics, this abstract freedom to recolor the mathematical description of a field at every point in space while keeping the physics consistent turns out to have an astonishing consequence. To make the theory respect this local symmetry, you are forced to introduce a new field that mediates an interaction between particles. This isn't just a mathematical trick, it is a generative principle. The requirement of local gauge symmetry literally creates the force fields we observe in nature. The electromagnetic force, which governs the behavior of light and charged particles, emerges naturally from requiring a certain kind of phase symmetry in the equations of quantum mechanics. The strong nuclear force which glues quarks together inside protons and neutrons, and the weak nuclear force responsible for radioactive decay, both arise from more complex but similar gauge symmetries. In this breathtaking framework, the fundamental forces aren't just described by beautiful mathematics. They are summoned into existence by the imperative of mathematical beauty itself. Perhaps the most successful and deeply tested symmetry principle is Lorentz invariance, the cornerstone of Einstein's special relativity. This is the statement that the laws of physics remain identical for all observers moving at constant velocity relative to each other. Whether you are standing still or cruising in a jetliner, every experiment you perform will yield the same result. This symmetry isn't just about motion. It fundamentally unites space and time into a single four-dimensional fabric called spacetime. The incredible predictions of special relativity time dilation, where moving clocks tick slower, length contraction, where objects shrink in their direction of motion, and the universal speed limit of light, all flow directly from the unwavering demand of Lorentz symmetry. It is a constraint so powerful that it dictates the very form that all physical laws must take. Any theory that violates this symmetry is immediately dismissed because our universe at its core does not have a preferred state of motion. There is no absolute rest frame. The cosmos provides no center stage audience seat. This profound democracy of observers, where no constant velocity perspective is privileged, is woven into the deepest structure of physical law, ensuring that the universe's rules are the same for everyone, everywhere. The symmetry story reaches its pinnacle with what many physicists consider the most sacred principle of all, CPT symmetry. This is the combined symmetry of charge conjugation C, parity P, and time reversal T. Individually, these symmetries can be violated. Charge conjugation means replacing every particle with its antiparticle. Parity means reflecting the universe as if in a mirror, swapping left for right. Time reversal means running the clock backward. We know from experiment that the weak nuclear force violates both parity and charge parity symmetry on their own. But the astonishing thing is that the combined operation of all three swapping particles for antiparticles, reflecting the universe in a mirror, and reversing the direction of time, appears to be an exact symmetry of all known physical laws. If you take any possible process in the universe and perform this full CPT operation, the result is another process that is equally valid and obeys the same physical rules. This has a profound implication. It means that a movie of an antiparticle living in a mirror universe where time flows backward would be completely indistinguishable from a movie of a normal particle in our universe. CPT symmetry is so deeply embedded in our theories that if it were ever found to be violated, it would necessitate a complete overhaul of the foundations of quantum field theory and relativity. It stands as a testament to the incredible order and self-consistency of the cosmic rulebook. This pervasive and deep-seated reliance on symmetry principles forces us to confront a question that borders on the metaphysical. Why is the universe so deeply, profoundly beautiful? This isn't a superficial beauty, but an elegant, mathematical beauty that seems to be the primary guiding force in the construction of physical law. The symmetries we've explored are not just convenient tools for calculation. They appear to be the fundamental architects of reality. This leads some physicists and philosophers to wonder if this beauty is a lucky accident, a happy coincidence that emerges from a more fundamental and perhaps less elegant underlying reality. Or is it indicative of a deeper truth that the universe is ultimately mathematical and aesthetic at its core? That beauty is not in the eye of the beholder, but is an objective feature of the cosmos, a compass that has guided its evolution and the formulation of its laws. The fact that we, products of this universe, have evolved the capacity to not only discover but also appreciate this deep beauty adds another layer of wonder to the mystery, suggesting that our search for understanding might be a conversation with a cosmos that is not only rational but also inherently graceful. But even if we accept that space, time, and the laws themselves might be emergent, we are still left with a monumental puzzle. Why did the universe begin in such a spectacularly specific and improbable state? This is the problem of initial conditions, and it brings our focus squarely back to the very first moment of the Big Bang. The cosmos didn't just need the right laws to produce us, it needed a perfect starting configuration, a set of initial parameters so precisely tuned that their probability is virtually zero. Imagine setting out on a cross-country road trip. The laws of physics are like the rules of the road and the mechanics of your car. But if you start your journey facing a concrete wall or perched on the edge of a cliff, no set of perfect driving laws will get you anywhere. The Big Bang presented a similar problem. For the universe to evolve into the complex, structured cosmos we see today, its launch had to be exquisitely precise in three key ways: its density, its uniformity, and its rate of expansion. The most striking of these is the density problem, often called the flatness problem. The universe appears to be almost perfectly flat on the largest scales, meaning that the density of matter and energy is exquisitely balanced against the expansion rate. This critical density is a razor's edge. If the universe had been even slightly denser at the beginning, the extra gravity would have caused it to recollapse into a big crunch almost immediately after the Big Bang, long before any stars or galaxies could form. If it had been even slightly less dense, the expansion would have been so rapid that matter would have flown apart too quickly to ever clump together into stars and planets. The universe would have become a cold, thin, and eternal void. The degree of fine-tuning required here is mind-boggling. For the universe to have survived for 13.8 billion years and produced galaxies, it must have begun with a density tuned to within 1 part in 10 to the power of 60 of the critical value. This is a 1 followed by 60 zeros, a number so incomprehensibly large that it makes every lottery ever won throughout human history look like a statistical certainty by comparison. Then there is the horizon problem, a puzzle concerning the universe's incredible uniformity. Look up at the night sky in any direction, and the cosmic microwave background radiation. The faint afterglow of the Big Bang is almost exactly the same temperature. This presents a profound causality issue. The universe simply hasn't existed long enough for light or heat or any form of information to have traveled from one distant region to another to equalize their temperatures. It's as if you walked into a vast concert hall and found thousands of people you've never met all humming the same note in perfect pitch, without any of them ever having communicated with each other. According to the standard Big Bang model, these regions should never have been in contact, so how did they coordinate their properties so perfectly? This smooth, uniform starting state is another incredibly special and unlikely initial condition that demands an explanation. These two profound problems, the inexplicable flatness and the causally disconnected uniformity, pushed cosmologists to search for a mechanism that could naturally create such a perfect starting point. The answer, proposed by physicist Alan Guth in 1980, was cosmic inflation. Guth's brilliant insight was that a tiny fraction of a second after the beginning, the universe underwent a period of hyper-expansion, ballooning in size by a factor of at least 10 to the 26 in a vanishingly small span of time. This inflationary spurt provides an elegant solution to both problems. Think of the flatness issue. Inflating the universe is like taking a tiny, crumpled piece of paper and blowing it up to the size of a continent. No matter how curved or wrinkled the original paper was, the expanded surface will appear perfectly flat to a tiny ant walking on it. Inflation does the same to spacetime, stretching any initial curvature so dramatically that the observable universe appears perfectly flat to us. For the horizon problem, inflation provides a beautiful causal mechanism. Before inflation, the entire observable universe was crammed into a tiny, subatomic volume that was easily small enough for everything to be in thermal contact, merrily exchanging heat and reaching a uniform temperature. Then, inflation took this tiny, homogeneous patch and stretched it to a size far larger than our entire observable cosmos. The regions we now see on opposite sides of the sky were once intimately connected neighbors, which explains why they share the same temperature and properties. Inflation didn't just make the universe big, it made it big from a very small, well-mixed and coherent beginning, solving the causality dilemma. Guth's initial model was a triumph, but it soon became clear that inflation itself introduced a new fine-tuning problem. To start, and more importantly, to stop correctly, the inflationary field required its own very specific properties. The energy landscape of this field had to be just right, a gentle slope that could provide the prolonged, powerful push needed for exponential expansion, followed by a quick drop to convert that inflationary energy into the hot soup of particles we know as the Big Bang. This process, called reheating, had to be incredibly efficient to produce the matter-filled universe we see. Furthermore, quantum fluctuations during this rapid expansion are believed to have been stretched to cosmic sizes, becoming the seeds for all the large-scale structure in the universe, the galaxies and galaxy clusters we see today. This is a profound success, but it means the specific details of inflation dictated the initial pattern of all cosmic structure. The great mystery that remains is why the inflationary field had the exact properties it did. What set the initial conditions for inflation itself? This pushes the fine-tuning problem back one step further, from the Big Bang to whatever mechanism triggered inflation, leaving us to wonder if we have truly explained the universe's special beginning or merely hidden it behind a new, equally mysterious curtain. Just when we thought we had a handle on the universe's grand narrative, a discovery at the very end of the 20th century completely upended our understanding of cosmic destiny. For decades, the central question in cosmology had been a simple one: is the universe open or closed? Would the collective gravity of all matter eventually halt the expansion from the Big Bang and pull everything back together in a fiery big crunch? Or would the expansion continue forever, gradually slowing as the cosmos cooled into a dark, eternal freeze? The answer, discovered by two independent teams of astronomers in 1998, was neither. The universe wasn't slowing down at all. Against all gravitational expectations, the expansion of the cosmos is accelerating. It is speeding up as if pushed by some mysterious, unseen force that we now call dark energy. This wasn't just a new discovery, it was a fundamental shock to our understanding of physics, revealing that roughly 70% of the universe's energy budget is composed of something we cannot see, do not understand, and never predicted. The story of this revelation is a masterpiece of scientific detective work. The teams, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, were using the most powerful telescopes on Earth to observe distant supernovae. These particular stellar explosions, known as Type 1, a supernova, are invaluable because they all explode with nearly the same intrinsic brightness. This makes them perfect standard candles. If you know how bright something truly is, you can measure how bright it appears from Earth and accurately calculate its distance. By looking at supernova in galaxies billions of light years away, the astronomers were effectively looking billions of years into the past. They expected to see that the expansion of the universe was decelerating over time due to the relentless pull of gravity. Instead, their data showed the opposite. The most distant and therefore oldest supernova were fainter than they should have been if the expansion had been constant. Their light had traveled farther than anyone had anticipated, meaning the universe had expanded more in that time than any model predicted. The only possible explanation was that the expansion rate was increasing. Adam Rees later described the moment of realization as a true heart-in-your-throat experience, a mix of terror and exhilaration at seeing a result that defied all conventional wisdom. For this paradigm-shattering work, Perlmutter, Schmidt, and Rees were awarded the Nobel Prize in Physics in 2011. So what is this dark energy? The leading and simplest explanation resurrects an old idea from Einstein himself, the cosmological constant. When Einstein was formulating his theory of general relativity, his equations suggested the universe should be either expanding or contracting. But the scientific consensus at the time, including his own belief, was that the universe was static and eternal. To force his equations to describe a stationary cosmos, he introduced a fudge factor, denoted by the Greek letter lambda. This cosmological constant represented a repulsive form of gravity, a kind of anti-gravity that could perfectly balance the attractive pull of matter, holding the universe in a steady state. When Edwin Hubble later discovered the universe was indeed expanding, Einstein famously called the cosmological constant his greatest blunder, and it was discarded for decades. The discovery of the accelerating expansion brought lambda back from exile with a vengeance. In this modern view, the cosmological constant is not a mathematical error, but a real feature of the vacuum of space itself. According to quantum physics, empty space is not truly empty. It is a seething, bubbling foam of virtual particles that constantly pop in and out of existence. This quantum frenzy should endow every cubic centimeter of vacuum with a certain energy, known as vacuum energy. This energy would have a repulsive gravitational effect, causing spacetime itself to expand. This vacuum energy is the prime candidate for what we call dark energy. Herein lies what is perhaps the most extreme fine-tuning problem in all of physics. When theorists attempt to calculate the expected value of this vacuum energy from first principles in quantum field theory, they get a number that is absurdly, catastrophically large. The calculation suggests the cosmological constant should be around 120 orders of magnitude stronger than what we observe. That's a 1 followed by 120 zeros. A universe with that much repulsive energy would have blown itself apart instantly after the Big Bang, tearing atoms to shreds before they could even form. There would be no stars, no planets, no possibility for life. Yet our universe has just a tiny, non-zero whisper of this energy, enough to gently nudge the galaxies apart over billions of years, but not so much that it prevents the gravitational collapse that forms galaxies in the first place. The value we observe is incredibly small, but it is not zero. If it were zero, the universe would not be accelerating. The fact that it has this exquisitely precise, tiny positive value seems like the most unlikely coincidence imaginable. It is as if a cosmic dial controlling the energy of empty space was set to a value that is 0 to 119 decimal places, and then a 1 is placed at the 120th decimal. This is a level of precision that defies any notion of random chance, presenting a fine-tuning puzzle that makes the others we've discussed seem almost trivial by comparison. To grasp the profound weirdness of this phenomenon, imagine a simple analogy. Picture throwing a ball straight up into the air. You expect gravity to slow it down, bring it to a stop at its peak, and then pull it back to Earth. This is how everyone expected the universe to behave after the Big Bang. The discovery of dark energy is the equivalent of throwing that ball into the air and watching it not only ignore gravity but suddenly shoot upward faster and faster into the sky, as if it had its own internal rocket. This isn't just an unknown force, it's a force that behaves in a way that turns our intuitive understanding of gravity on its head. It acts as a form of cosmic repulsion, a pressure inherent to the fabric of space that grows stronger as the universe expands and provides more space. This is why its effects only became dominant a few billion years ago. For the first half of the universe's history, matter was denser and its gravitational attraction was the dominant force. Only after the universe had expanded and diluted enough did dark energy's repulsive push finally overcome gravity's pull and begin to accelerate the expansion. This adds another profound and unexplained parameter to the universe's rulebook. Not only are the strengths of the forces and the masses of the particles finely tuned, but the very energy of the void itself is set to a miraculously specific value. This deepens the central mystery exponentially. In the context of the multiverse, perhaps an infinite number of universes have random values for their cosmological constants, and we simply inhabit one of the incredibly rare bubbles where the value is small enough to allow for galaxies and life. For theories like cosmic natural selection, it's harder to see how a universe's ability to produce black holes would be optimized by having a small positive cosmological constant. Some physicists have explored the possibility that dark energy is not a constant after all, but a dynamic field that evolves over time, nicknamed quintessence. Yet, even these models simply exchange one fine-tuned parameter for another, pushing the mystery into the properties of that new field. The enigma of dark energy stands as a monumental reminder of how much we still have to learn about the fundamental rules of reality, revealing that the cosmos is not just expanding but is doing so under the influence of a mysterious, dominant force whose origin and nature remain one of the greatest unsolved puzzles in science. While dark energy acts as a mysterious force pushing the cosmos apart on the grandest scales, another profound and invisible presence dominates the universe in a completely different way, sculpting the very architecture of reality itself. This is the enigma of dark matter, an unseen form of mass that does not emit, absorb, or reflect any light, yet whose gravitational influence is the primary architect of the cosmic structures we observe. The evidence for this shadowy component of the universe is not based on what we can see, but on how the things we can see are compelled to move. The story begins not in deep space, but in the 1930s with a brilliant and irascible astronomer named Fritz Zwicky, working at the California Institute of Technology. Zwicky was studying the Coma Cluster, a vast collection of over 1,000 galaxies bound together by gravity. By measuring the velocities of these galaxies as they orbited the cluster's center, he made a startling discovery. The individual galaxies were moving so incredibly fast that the collective gravity of all the visible stars and gas in the cluster should have been utterly insufficient to hold them together. According to all known physics, the Coma Cluster should have flown apart eons ago. Zwicky concluded that there must be a huge amount of unseen matter providing the extra gravitational glue, matter he called dunkle materie, or dark matter. His colleagues largely dismissed the idea, attributing it to Zwicky's notoriously combative personality and unconventional methods. It would take another 4 decades for the evidence to become undeniable, thanks to the meticulous work of astronomer Vera Rubin and her colleague Kent Ford. In the 1970s, Rubin was studying the rotation of individual spiral galaxies. According to Newtonian gravity, stars on the outer edges of a galaxy, far from the central bulge of mass, should orbit much more slowly than stars closer to the center. This is exactly what we see in our solar system. Pluto, the most distant planet, crawls along at a snail's pace compared to Mercury, which whips around the Sun at blistering speed. But when Rubin measured the orbital velocities of stars in the Andromeda galaxy, she found something that defied this expectation. Stars at the very outskirts of the galaxy were orbiting just as fast as those near the center. The only way this could happen is if the galaxy was enveloped in a massive, invisible halo of matter that extended far beyond the visible edge of the stars, providing additional gravitational pull to keep those outer stars whirling at high speed. This data, the now famous flat galaxy rotation curve, was the smoking gun that convinced the astronomical community that Zwicky had been right all along. The universe is filled with something we cannot see. This gravitational evidence is powerfully complemented by a phenomenon predicted by Einstein's general relativity: gravitational lensing. The mass of dark matter warps the very fabric of spacetime around it. When light from a distant galaxy travels through this warped region on its way to our telescopes, its path is bent, much like light passing through a lens. By studying how the images of background galaxies are distorted and magnified by the foreground mass of a galaxy cluster, astronomers can literally map the distribution of dark matter. These maps reveal an astonishing cosmic skeleton. Dark matter forms a vast, intricate web throughout the universe with dense knots and long filaments. The familiar galaxies of stars and gas are merely the visible ornaments hanging on this invisible scaffolding, forming only in the densest clumps of the dark matter web. Without this underlying structure, the universe would be a much smoother, far less interesting place. The gravitational pull of dark matter provided the initial seeds that allowed ordinary matter to clump together, eventually collapsing to form the first galaxies and stars. In a very real sense, we owe our existence to this unseen cosmic architect. So what exactly is dark matter made of? We know what it is not. It is not made of atoms, the protons, neutrons, and electrons that constitute everything we see around us, known collectively as baryonic matter. It does not interact with light or with other matter through the electromagnetic force, which is why it is perfectly transparent and frictionless. The leading theoretical candidate is a hypothetical particle known as a WIMP, a weakly interacting massive particle. These particles would be heavy, slow-moving, and would interact with normal matter only through gravity and the weak nuclear force, making them incredibly difficult to detect. For decades, physicists have been conducting extraordinarily sensitive experiments deep underground, in abandoned mines and tunnels, to shield them from cosmic rays. They use huge vats of ultra-pure liquid xenon or other materials, hoping that on very rare occasions, a passing dark matter particle will bump into an atomic nucleus and create a tiny, measurable signal. So far, these direct detection experiments have not yielded a definitive discovery, but they have progressively ruled out large swaths of possible properties for WIMP, narrowing the search. Other candidates are also in the running. Actions are another theoretical particle, predicted for different reasons in particle physics, that could be incredibly light but exist in such vast numbers that they account for the dark matter. There are even more exotic ideas, like the possibility that dark matter is not a particle at all but a property of gravity itself that manifests only on the largest cosmic scales, requiring a modification of Einstein's theory. However, the success of general relativity in so many other tests makes this alternative less appealing to most physicists. The properties of dark matter, whatever it is, appear to be exquisitely fine-tuned for the task of building a universe like ours. If dark matter interacted more strongly with itself and with normal matter, it would be sticky. It would lose energy, collapse too efficiently, and form overly dense clumps that could disrupt the formation of galaxies or even prevent planets from safely orbiting stars. If it were too hot, meaning its particles moved at velocities close to the speed of light, its tendency to stream freely would have smoothed out the early universe too much, preventing the gravitational collapse that seeds galaxies. The fact that dark matter is cold or slow-moving and collisionless seems to be a perfect prescription for gently gathering ordinary matter into the beautiful structures we see. This adds yet another layer to the cosmic fine-tuning puzzle. Not only are the constants of nature perfectly set, but the very ingredients of the cosmos also include a mysterious, invisible component whose specific properties were crucial for creating a universe capable of hosting life. Yet for all its spectacular predictive power, the Standard Model presents us with a profound, and to many physicists, deeply unsatisfying mystery. The theory's framework is not built from a single, elegant equation that dictates all its properties. Instead, it functions more like a complex and incredibly precise machine that requires 19 separate, fundamental numbers to be manually input before it can run. These are the Standard Model's free parameters, 19 knobs on the cosmic control panel that must be carefully tuned by hand, their values determined not by the theory itself, but by painstaking experiment. They are the arbitrary inputs that make the magnificent outputs possible. Think of it like a masterfully engineered car that can take you anywhere, but only after you first tell it the exact values for the density of gasoline, the tensile strength of steel, and the electrical conductivity of copper. The car works perfectly, but you are left wondering why those specific numbers are what they are. This is the curious position of modern particle physics. We have a machine that describes the fundamental constituents of reality with unbelievable accuracy, but we have no idea why its core settings are what we measure them to be. These 19 parameters cover the entire spectrum of the subatomic world. Among them are the masses of the fundamental particles. Why does the top quark weigh as much as a gold atom, while the electron is almost 200,000 times lighter? Why is the neutrino so incomprehensibly lightweight, a feather on the cosmic scales? The theory provides no answer. It simply accepts these values as facts of nature. Then there are the coupling constants, which determine the strength of the fundamental forces. The fine structure constant dictates the power of the electromagnetic force, while its counterparts govern the strong and weak nuclear forces. These values are not derived from any deeper principle. They are measured and then plugged into the equations. Perhaps the most bizarre set of parameters are those found in the Kabibbo-Kobayashi-Maskawa or CKM matrix. This mathematical construct describes how quarks change from one type to another through the weak nuclear force, a process essential for the nuclear reactions that power the sun. The matrix contains mixing angles and a complex phase, numbers that essentially quantify the probability that a down quark will turn into an up quark, or a strange quark will become a charm quark. These values appear completely random, like a set of arbitrary lottery numbers that just happened to be drawn. If they were even slightly different, the universe would be a radically different place, potentially unable to form stable atoms or sustain the long-lived stars necessary for life. This arbitrariness at the heart of our most successful physical theory has long been a source of frustration for physicists who seek not just to describe nature, but to understand it. The Nobel laureate Steven Weinberg articulated this feeling perfectly when he said of the Standard Model, "It's a very good theory, it's just that we're not entirely satisfied with it because it has too many arbitrary features." Too many free parameters. He compared it to learning the vocabulary of a language without knowing its grammar. We have memorized the words, the particle masses, the force strengths, but we have no grasp of the underlying syntax that would explain why these words were chosen and not others. The dream is to find a deeper theory, a more fundamental grammar, from which these 19 numbers would naturally flow as necessary consequences, not as arbitrary inputs. This quest for a final theory is driven by the belief that the universe is ultimately rational and comprehensible, not built on a foundation of random, inexplicable digits. To appreciate the strangeness of this situation, imagine a vast and incredibly sophisticated radio. You can turn its 19 dials to specific, precise positions, and when you do, it picks up a perfectly clear, static-free transmission describing all of visible reality. But you have no idea why those particular dial settings work. You found them through trial and error, and they work magnificently, but the radio's instruction manual is missing the page that explains why the dials are calibrated the way they are. The Standard Model is that radio. We know the settings that work, but the reason why they work, why the masses and forces have the values they do, remains the deepest and most important unsolved problem in fundamental physics. It represents another layer of the universe's unwritten rules, a set of numerical constants that appear to be just as finely tuned for our existence as the cosmological parameters of the cosmos itself, yet whose origin is even more mysterious because they operate at the very bedrock of material reality. Faced with this frustrating arbitrariness at the heart of the Standard Model, physicists began a monumental quest for a more fundamental theory, one that could derive these 19 mysterious numbers from a single, elegant principle rather than leaving them as unexplained inputs. This search for a deeper unity has led to two of the most ambitious and mathematically sophisticated frameworks in all of science: supersymmetry and string theory. The journey begins with a breathtakingly beautiful idea known as supersymmetry, or SUSY for short. This theory proposes a profound and intimate partnership between the two great families of particles that make up the universe, the fermions and the bosons. Fermions are the particles of matter, like electrons and quarks, which have half-integer spin and obey the Pauli exclusion principle, meaning they can't occupy the same quantum state. This is why matter is solid. It's why you don't fall through your chair. Bosons, on the other hand, are the force carriers like photons and gluons, which have integer spin and love to congregate in the same state. This is how forces are transmitted. Supersymmetry proposes that for every known fermion, there exists a superpartner boson, and for every known boson, a superpartner fermion. The electron, a fermion, would be paired with a selectron, a boson. The photon, a boson, would be paired with a photino, a fermion. This elegant symmetry would effectively double the number of elementary particles, but in doing so, it would solve some of the most vexing problems in physics. The most compelling motivation for supersymmetry is the hierarchy problem, which concerns the astonishing weakness of gravity compared to the other fundamental forces. Gravity is a staggering 10 to the 36 times weaker than the electromagnetic force. This is a difference of a trillion. Why is there such an enormous gap between the strength of gravity and the other forces? In the Standard Model, this problem manifests when we try to calculate the mass of the Higgs boson. The Higgs mass is extremely sensitive to quantum fluctuations from any other particle that interacts with it. These fluctuations, if left unchecked, would naturally want to drive the Higgs mass up to the enormous Planck scale, which is 16 orders of magnitude heavier than its actual measured value. This would make the Higgs impossibly heavy and break the entire electroweak symmetry that gives particles their mass. To get the correct light Higgs mass we observe, physicists would have to artificially and with unbelievable precision fine-tune these enormous quantum corrections to cancel each other out to 34 decimal places. This is an aesthetic and philosophical nightmare for theorists. Supersymmetry provides a stunningly elegant solution because it pairs fermions with bosons. The quantum fluctuations from a fermion and its superpartner boson come with opposite signs. They are perfectly poised to cancel each other out automatically, protecting the Higgs mass and solving the hierarchy problem without any need for miraculous fine-tuning. It's a natural consequence of the symmetry itself. Furthermore, supersymmetry allows for the unification of the three fundamental forces of the Standard Model: the electromagnetic, weak, and strong forces. At high energies, their respective coupling constants, which have different strengths at everyday energies, beautifully converge to a single value in supersymmetric models, suggesting they were all once aspects of a single, unified force in the early universe. This grand unification is a powerful theoretical law. For decades, physicists were supremely confident that supersymmetry would be discovered. The Large Hadron Collider was designed, in part, to be a supersymmetry factory, expected to produce these exotic superpartners in abundance. Yet, as the collider has collected more and more data, the expected signatures have failed to materialize. No selectrons, no photinos, no squarks have shown themselves. This non-discovery represents one of the biggest surprises and disappointments in modern physics. If supersymmetry is real, it must be a broken symmetry, meaning the superpartners are far heavier than initially hoped. This pushes them beyond the current energy reach of our colliders and to some extent undermines the naturalness argument that made supersymmetry so attractive in the first place. The elegant cancellation that solved the hierarchy problem now requires its own kind of fine-tuning if the superpartners are extremely massive. The physics community now finds itself at a crossroads, forced to consider that nature may not care about our aesthetic desire for naturalness, or that supersymmetry might manifest in a way we haven't yet imagined, or that we must look elsewhere for a deeper unity. This search for a more complete theory naturally leads us to an even more radical and ambitious framework: string theory. If supersymmetry proposes a new relationship between particles, string theory proposes a revolution in what those particles actually are. The central idea is as simple as it is profound. The point-like particles of the Standard Model are not actually points. Instead, they are tiny, vibrating, one-dimensional loops of energy called strings. Each different vibration mode of a string corresponds to a different particle. One specific vibration gives you an electron, another gives you a photon, another a quark. In this elegant picture, the bewildering zoo of elementary particles is unified into a single fundamental object, a string whose various harmonies compose the symphony of the universe. The mathematics of string theory is not only beautiful but also compellingly inevitable. For the theory to be mathematically consistent, these strings must vibrate in a 10-dimensional spacetime. Furthermore, one of the vibration modes of the string turns out to have exactly the properties of the graviton, the hypothetical particle that mediates the force of gravity. This was a monumental achievement. String theory didn't just include gravity, it demanded it. For the first time, a framework emerged that could seamlessly weave quantum mechanics and general relativity into a single, coherent tapestry of physics, a long-dreamed-of theory of everything. The development of string theory reached a pivotal moment in the 1990s, often called the second superstring revolution, largely driven by the work of mathematician and physicist Edward Witten. Witten and others discovered that the 5 different versions of string theory that had been developed were not actually competing theories, but were instead different limiting cases of a single, deeper, 11-dimensional theory called M-theory. The M could stand for magic, mystery, membrane, or matrix. Its full nature remains one of the great unsolved problems in theoretical physics. M-theory introduced the concept of brains, multidimensional objects upon which strings could end. Our entire universe could be a 3-dimensional brain floating in a higher dimensional bulk. This vision dramatically expanded the possibilities of the theory. However, this incredible mathematical power comes with a devastating cost: the landscape problem. The extra dimensions required by string theory must be curled up or compactified into a tiny, complex shape. The geometry of this shape determines the physical laws that low-energy observers like us would experience, the values of those 19 arbitrary constants, the masses of particles, the strengths of forces. The problem is that there are a staggering number of ways to curl up these extra dimensions, perhaps 10 to the 500 or more different possible configurations. Each configuration corresponds to a different universe with completely different physical laws. This is the string theory landscape, a vast, abstract terrain of possible universes. Instead of providing a unique prediction for our universe's parameters, string theory seems to predict a multiverse of possibilities, a cosmic casino where every possible set of rules is realized somewhere. This returns us to the anthropic principle. We simply live in one of the rare universes where the compactification happened to produce laws compatible with our existence. For many physicists, this feels like a retreat from the original goal of explanation. We sought a theory that would tell us why the constants must be what they are, and instead we got a theory that says they could be almost anything, and we just got lucky. The ongoing scientific struggle is palpable, a tension between the breathtaking mathematical beauty of these frameworks and their current inability to make unique, testable predictions for our world. The dream of a final theory that explains all the rules from a single, elegant principle remains just that, a dream, compelling us to continue the search for even deeper truths about the architecture of reality. Alan Guth's brilliant insight into cosmic inflation was a true masterstroke of theoretical physics, providing elegant and powerful solutions to 2 of cosmology's most stubborn puzzles. It explained the universe's impossible flatness by stretching any initial curvature to near perfection, much like smoothing out the wrinkles on a balloon as it inflates. It solved the horizon problem by positing that the entire observable universe was once a tiny, causally connected patch that was then blown up to cosmic size, accounting for the uniform temperature we see in all directions. But perhaps its most astonishing success was a prediction it made almost as an afterthought. The same quantum mechanics that govern subatomic particles would also be at play during inflation. The hyper-expansion of space would stretch microscopic quantum fluctuations in the inflationary field itself, magnifying them to macroscopic proportions and imprinting them onto the fabric of the cosmos. These tiny ripples in density became the gravitational seeds for all future structure, the eventual galaxies, galaxy clusters, and the vast cosmic web we observe today. This prediction was spectacularly confirmed by detailed maps of the cosmic microwave background, which show a pattern of hot and cold spots that match the predictions of inflationary theory with stunning precision. It was a triumph, a theory that not only solved existing problems, but also made a new, successful prediction about the very large-scale structure of the universe. Yet, this incredible success came with a hidden and profound cost. As physicists like Andre Linde delved deeper into the mechanics of inflation, they realized that the process, once started, might be practically impossible to stop everywhere at once. This is the concept of eternal inflation. The inflationary field is thought to have a complex energy landscape with hills and valleys. For inflation to end and transition into the hot Big Bang we know, the field must roll down into a valley and settle at its minimum energy. However, due to quantum fluctuations, this process is not uniform. In some regions of space, the field will indeed fall into a valley and inflation will cease, giving rise to a pocket universe like our own. But in other regions, quantum jumps will keep the field on a high-energy plateau, causing inflation to continue at an exponential rate. These ever-inflating regions spawn new pocket universes at a furious pace, each with the potential for its own unique set of physical constants and laws, depending on exactly how its local inflation ended. The single, cohesive universe of classical cosmology was suddenly replaced by a vast, frothing multiverse, a cosmic foam of bubbles with potentially different physics, forever separated by unimaginably vast stretches of still inflating space. This leads us to a deeply ironic and meta twist in our story. Inflation was originally proposed to explain the incredible fine-tuning of the universe's initial conditions, the special, low entropy state that allowed for our existence. But now we must ask, is the inflationary mechanism itself fine-tuned? To produce the universe we see, the inflationary field needed very specific properties. Its energy slope had to be shallow enough to allow for a sufficiently long period of exponential expansion, yet it had to be steep enough to eventually end and efficiently convert its energy into particles during the reheating phase. If the slope were too steep, inflation would end too quickly, failing to solve the flatness and horizon problems. If it were too shallow, the quantum fluctuations might be too large, creating an universe far too lumpy and chaotic for galaxies to form. The properties of the field itself, its potential energy shape, appear to be yet another set of dials on the cosmic control panel that must be set to very precise values to get a universe like ours. We seem to have solved one fine-tuning problem only to discover another, pushing the mystery back a step from the universe's birth to the laws that govern the inflationary epoch itself. This creates a fascinating and almost philosophical loop. We invoke a mechanism like inflation to explain the apparent fine-tuning of our cosmos, but that very mechanism itself requires a certain degree of fine-tuning to work correctly. It's as if we explained the existence of a perfectly tuned watch by pointing to a watchmaker, but then had to explain why the watchmaker had such exquisitely steady hands and perfect eyesight. The multiverse concept, which emerges so naturally from eternal inflation, is often offered as a solution to this new fine-tuning problem. In an infinite multiverse, every possible value for the inflationary parameters is realized somewhere. We simply find ourselves in one of the bubbles where the parameters were just right to allow for our kind of universe, yet this feels to some like an explanatory retreat. It exchanges a puzzle about our single universe for a vast, untestable ensemble of universes, and it still leaves open the question of why the overarching mechanism that generates the multiverse, the meta-laws of eternal inflation, are themselves conducive to producing any life-permitting universes at all. The quest for a final explanation seems to recede into an infinite regress, with each proposed solution unveiling a new, deeper layer of mystery about why the rules of the game exist in this particular, life-allowing form. But if the universe's fundamental parameters present a deep mystery, the conflict between our two most successful theories of reality represents an even more profound schism at the heart of physics. For nearly a century, we have lived with a cosmic divided house. In one wing, we have general relativity, Albert Einstein's magnificent description of gravity as the curvature of spacetime itself. It is a theory of the very large of planets, stars, and galaxies, painting a picture of a smooth, continuous, and deterministic cosmic fabric. In the other wing, we have quantum mechanics, the astonishingly accurate rules governing the atomic and subatomic world. It is a theory of the very small, of particles and forces, depicting a reality that is granular, probabilistic, and inherently fuzzy. Both theories are spectacularly successful in their own domains, passing every experimental test with flying colors. Yet they are fundamentally, philosophically, and mathematically incompatible. Unifying them into a single theory of quantum gravity is perhaps the greatest and most elusive goal in all of modern physics, a conundrum that forces us to question our most basic assumptions about the nature of reality. The conflict becomes violently apparent in extreme environments where both immense gravity and tiny quantum scales must be considered simultaneously, nowhere more so than at the heart of a black hole. According to general relativity, when a massive star collapses, it forms a singularity, a point of infinite density where the known laws of physics break down and spacetime itself ceases to exist. This singularity is hidden behind an event horizon, a point of no return from which not even light can escape. Quantum mechanics, however, throws a profound wrench into this seemingly clean picture through the black hole information paradox. One of the core principles of quantum theory is unitarity, the idea that information about a physical system is never truly lost. If you have complete information about a system now, you should, in principle, be able to use the laws of physics to calculate its state at any point in the past or future. But what happens when you throw a book containing information into a black hole? Stephen Hawking famously calculated that black holes are not completely black. They slowly radiate energy due to quantum effects near the event horizon. This Hawking radiation appears to be purely thermal, a featureless glow that depends only on the black hole's mass, charge, and spin. It contains no information whatsoever about the specific book or anything else that fell in. If the black hole eventually evaporates completely, disappearing from the universe, then the information contained in that book seems to have been irretrievably lost, violating a sacred rule of quantum mechanics. This paradox suggests that our understanding of either gravity, quantum physics, or both is fundamentally incomplete when pushed to their limits. Another deep fissure between the two theories concerns the nature of time itself. In general relativity, time is dynamic and malleable. It is woven into the four-dimensional fabric of space-time, and it can be stretched and warped by gravity and motion. Yet it remains a continuous background against which events unfold. In the standard formulation of quantum mechanics, however, time is treated as an absolute external parameter. It is not a quantum operator itself. It is the classical stage on which the quantum wave function evolves. This is known as the problem of time in quantum gravity. When we try to combine the theories, we are trying to merge a dynamic plastic time with a fixed classical time, and they simply don't fit together. In some approaches to quantum gravity, like the Wheeler-DeWitt equation, time vanishes from the fundamental description altogether, suggesting that our perception of a flowing time might be an emergent illusion derived from a more fundamental, timeless reality. This is a concept so alien to our experience that it highlights the sheer conceptual gulf we must bridge. Faced with this monumental challenge, physicists have pursued several ambitious paths. One major route is loop quantum gravity. This approach takes the lessons of general relativity seriously from the start. It proposes that space itself is not smooth and continuous, but is instead composed of tiny, discrete, loop-like quanta of volume. Imagine the fabric of spacetime not as a perfectly smooth sheet, but as an incredibly fine mesh or a weave of a billion tiny threads. These loops of space form a network called a spin network, and the evolution of this network over time describes the dynamics of the universe. In this theory, the dreaded singularity at the center of a black hole is replaced by a quantum bounce, where the crushing gravity eventually gives way to a repulsive force, potentially spewing the compressed matter out into a new region of spacetime. Loop quantum gravity is a beautiful and deeply geometric approach, but it has struggled to show how the familiar smooth spacetime of general relativity and the particles of the Standard Model naturally emerge from its fundamental loops. The other primary contender is, of course, string theory, which we've already explored for its unifying ambitions. String theory approaches the problem from the quantum side, proposing that the fundamental entities are not point particles but vibrating strings, and that gravity must be included for the mathematics to be consistent. Its great strength is its ability to naturally incorporate all known forces and particles. Its great weakness, as discussed, is the landscape problem and its current lack of testable predictions that would distinguish it from other ideas. Other intriguing ideas exist on the fringe. Causal set theory suggests that spacetime is fundamentally a discrete collection of events connected by cause and effect relationships. Asymptotically safe gravity posits that gravity might be reconciled with quantum mechanics without needing new particles or extra dimensions, if the strength of gravity approaches zero at extremely high energies. The ongoing struggle to marry these two pillars of physics reveals something profound. It is not merely a technical problem of conflicting mathematics. It is a clash of worldviews, a conflict between a universe that is smooth, continuous, and deterministic, and a universe that is granular, probabilistic, and observer-dependent. The fact that we have two such powerful, accurate, and yet incompatible descriptions of reality suggests that both are likely approximations of a deeper, more fundamental truth that lies beyond our current conceptual framework. Our failure to find a complete theory of quantum gravity after so many decades of effort is not a sign of scientific failure, but a beacon pointing toward a revolution in understanding. It humbles us, reminding us that the universe's ultimate rulebook may be written in a language we have not yet learned to speak, containing chapters on the nature of reality that we have not yet even imagined. While Max Tegmark's mathematical universe hypothesis offers a breathtakingly elegant vision of reality, it inevitably draws serious scrutiny from both physicists and philosophers who question whether this radical form of mathematical Platonism can truly hold up under pressure. One of the most immediate and profound challenges arises from the problem of consciousness. If our universe is truly just a mathematical structure, a vast, abstract equation existing in a timeless Platonic realm, then what are we? Our rich inner world of sensations, emotions, and subjective experience, the redness of a rose, the ache of sadness, the warmth of sunlight feels utterly alien to the cold, impersonal world of mathematical relations. How does a self-aware, conscious observer spontaneously arise from a set of equations? The theory seems to provide a magnificent description of the external, objective cosmos, but leaves the internal, subjective world of mind as a ghost in the machine, an inexplicable add-on to an otherwise purely mathematical reality. This is a modern incarnation of the ancient mind-body problem, now framed as the mind-math problem. If mathematical existence is the only kind of existence, then consciousness must somehow be a property of certain complex mathematical structures. But this feels to many critics like a leap of faith rather than a rigorous explanation. We have no mathematical theory of consciousness, no equation for qualia, And until we do, positing that consciousness is just another mathematical pattern feels like hand waving away the very thing that makes our reality feel real to us. This criticism is powerfully articulated by those who see a fundamental category error in equating mathematical description with physical existence. A map is not the territory. We can use mathematics to describe a hurricane with incredible precision, modeling its wind speeds, pressure gradients, and predicted path. But the mathematics is not the hurricane itself. It is a representation, a symbolic language we use to capture its behavior. The hurricane possesses a raw, physical existence. It has energy. It moves water. It destroys buildings that the equations themselves do not share. Critics argue that Tegmark is conflating the map with the territory. He is saying that because the map is perfectly detailed and isomorphic to the territory, the map is the territory. But this seems to ignore the nature of the substance being mapped. The physical world has a concrete, causal power that abstract mathematical objects, by their very nature, seem to lack. A triangle defined by 3 points in a Euclidean plane does not exert gravity. It does not interact with other mathematical shapes. It simply is. To say that our physical universe is that triangle or a more complex mathematical structure requires explaining how abstract relations acquire causal efficacy, how they transition from being descriptions to being the very stuff of reality. This is a philosophical hurdle the hypothesis has yet to satisfactorily clear. Even within the family, the hypothesis found a thoughtful critic. Harold Tegmark, Max's father and a professor of mathematics himself, raised a poignant and practical objection. He questioned how this vast, timeless landscape of mathematical structures could give rise to our specific, flowing experience of time and our seemingly unique historical narrative. If all mathematical structures exist equally, why do we find ourselves in this particular one, experiencing this moment right now with a clear past and an uncertain future? This connects to a deep technical issue known as the measure problem, which also plagues multiverse theories. In an infinite ensemble where everything exists, how do we assign probabilities? Why does it seem overwhelmingly more likely that we should be Boltzmann brains fleeting, self-aware fluctuations in a cosmic void rather than coherent beings embedded in a 13.8 billion-year-old universe? Without a way to define a probability measure on the landscape of mathematical structures, the theory struggles to explain why we observe the ordered, historically coherent reality that we do, rather than a chaotic, random, or fragmented one. Furthermore, the hypothesis creates a curious and perhaps untenable blurring of lines between different kinds of abstractions. If any self-consistent mathematical structure physically exists, then what about the mathematical structure that describes the plot of a novel? What about the mathematical structure of a highly detailed, self-consistent simulation? The theory seems to imply that every conceivable world, every fictional universe that can be described with logical consistency, must exist in the same fundamental sense as our own. This leads to a kind of ontological inflation that can feel absurd to many. It threatens to drain the word "exist" of any useful meaning. If a universe where gravity is repulsive and donkeys recite Shakespeare exists in the same way ours does, then we are left with a profoundly flat ontology where nothing is more real than anything else, which seems to contradict our basic intuition about our own experience being singular and immediate. Finally, the hypothesis faces the challenge of its own untestability. While it is a coherent and fascinating philosophical framework, it is difficult to see what empirical evidence could ever definitively confirm or refute it. Any physical observation we make, any law we discover, can be described as discovering the properties of the mathematical structure we are in. This makes the theory incredibly flexible, but also potentially unfalsifiable, a cardinal sin in the eyes of many scientists. It risks moving from being a scientific hypothesis to a metaphysical belief system, while it provides a stunning and provocative answer to the question of why mathematics is so unreasonably effective in describing the world. Its critics maintain that it does so at the cost of creating new, even deeper mysteries about consciousness, causality, and the nature of existence itself. This rigorous scrutiny is not a dismissal but a vital part of the scientific process, ensuring that even the most elegant and appealing ideas are subjected to the fire of debate, forcing us to refine our questions and deepen our search for a complete picture of reality. Yet for all its grand explanatory power, the multiverse hypothesis finds itself on the receiving end of some of the most pointed criticism in modern science, accused of stepping over a fundamental line that separates physics from metaphysics. The most damning charge leveled by prominent figures like Princeton physicist Paul Steinhardt is that these theories are ultimately untestable and therefore unscientific. This argument is rooted in the philosophy of science championed by Karl Popper, who asserted that for a theory to be considered scientific, it must be falsifiable. It must make specific predictions that could, in principle, be proven wrong by observation or experiment. If a theory is compatible with every possible outcome, it explains nothing. The concern is that the multiverse, by its very definition, places other universes permanently beyond our observational reach, separated by vast inflationary domains or different dimensional compactifications. Any observation we make in our universe can be explained by the anthropic principle. We see what we see because we exist. There is no conceivable observation we could make that would disprove the existence of other universes. As Steinhardt has powerfully argued, this makes the multiverse idea a theory of anything that predicts everything and therefore explains nothing, effectively abandoning the empirical method that has been the bedrock of scientific progress for centuries. This problem of empirical access creates a deep frustration for many experimentalists and theorists who seek concrete predictions. Nobel laureate David Gross has expressed this skepticism, questioning whether the multiverse is a part of science or a philosophical surrender. He points out that in the past, similar cosmological puzzles, like the initial low entropy of the universe, were eventually addressed by powerful new theories like inflation, rather than resorting to anthropic reasoning. The worry is that accepting the multiverse as an explanation for fine-tuning might stifle the search for a deeper, more fundamental theory that could actually derive our constants from first principles. Why bother looking for an elegant, unique solution if you can always fall back on the statistical coincidence of an infinite ensemble? This tension divides the physics community between those who see the multiverse as the next logical step in our understanding and those who see it as a premature capitulation, a retreat from the traditional goal of physics to find a single, compelling explanation for why our universe is the way it is. Beyond the scientific status, the multiverse hypothesis generates profound philosophical puzzles that challenge our very understanding of reality and our place within it. Perhaps the most notorious is the Boltzmann brain paradox, a thought experiment that emerges from statistical mechanics and becomes a nightmare scenario in an eternal multiverse. The physicist Ludwig Boltzmann once suggested that in a vast and eternal universe, the random fluctuations of particles could occasionally, by sheer chance, assemble a fully formed brain that briefly flickers into consciousness, complete with false memories of a life it never lived. In an infinite multiverse where anything that can happen will happen an infinite number of times, the number of these disembodied Boltzmann brains should vastly, overwhelmingly outnumber the number of ordinary, evolved observers like us who have a continuous existence in an ordered universe. Therefore, if the multiverse is real, the statistical probability suggests that you and I are far more likely to be a fleeting Boltzmann hallucination than a real person with a genuine past. This absurd conclusion is so philosophically unpalatable that many physicists see it as a major strike against the idea of an eternal, randomly fluctuating multiverse, forcing a re-evaluation of the initial conditions or the cosmological models that lead to such a prediction. This connects directly to the measure problem, which is perhaps the most technical but devastating challenge for multiverse theories. In an infinite ensemble of universes, how do you define probability? How do you count the number of universes with a given property? If there are infinitely many universes with life and infinitely many without, the ratio of life permitting to life prohibiting universes is undefined. To get any predictive power out of the multiverse, you need a way to count the universes, a probability measure. But there is no unique or obvious way to do this. Different choices for how you slice up the infinite ensemble can yield completely different answers, making any anthropic prediction hopelessly ambiguous. You could just as easily prove that a universe with our constants is probable as you could prove it is astronomically improbable, simply by choosing a different mathematical scheme for counting. This lack of a unique measure undermines the entire explanatory project of the multiverse, turning what seemed like a powerful statistical argument into a mathematical mirage. These critiques don't necessarily disprove the multiverse, but they reveal the immense conceptual price tag that comes with it, forcing us to confront whether this popular explanation for fine-tuning solves more problems than it creates, or simply exchanges one set of deep mysteries for another. Lee Smolens's theory of cosmic natural selection presents a profoundly elegant and Darwinian vision of reality, one where the laws of physics are not handed down from on high, but are forged in the fiery crucible of cosmic evolution. It's a narrative that resonates deeply with our understanding of biological complexity, suggesting that the universe's fine-tuning isn't for life, but for fecundity, for the ability to produce more black holes and, in doing so, more offspring universes. But after decades of consideration, where does this grand and imaginative proposal stand within the scientific community? The assessment is mixed, a fascinating blend of enduring intrigue and significant, perhaps even growing, challenges. The most immediate and persistent criticism is the stark lack of any direct evidence for the theory's core mechanism. For cosmic natural selection to function, black holes must serve as cosmic wombs. When a massive star collapses into a singularity, Smolens proposes that this point of infinite density doesn't mark a final end, but a bounce, a transformation into a new, expanding universe. This is a breathtaking idea, but it remains entirely speculative. Our current understanding of physics, encapsulated by Einstein's general relativity, breaks down completely at the singularity. To describe what truly happens there, we need a complete theory of quantum gravity, which we simply do not yet possess. Without this crucial piece of the puzzle, the concept of a black hole birth remains in the realm of compelling hypothesis rather than established physics. No observation has yet provided a hint that matter falling into a black hole does anything other than add to its mass and vanish from our universe forever. The theory's foundational premise is thus its greatest vulnerability, resting on physics that is still unknown. This leads directly to mathematical challenges. For the theory to work, the process of a black hole spawning a new universe must allow for slight mutations in the physical constants of the offspring. These random variations are the fuel for cosmic evolution. However, physicists have struggled to construct a robust mathematical framework that details precisely how the parameters of a parent universe are transferred and subtly altered during this hypothetical bounce. The mechanism of inheritance is murky. Furthermore, the theory predicts that our universe should exist at a local peak of fitness, meaning any tiny change to its constants should result in a universe that produces fewer black holes. Testing this prediction requires calculating how the number of black holes would change if, say, the mass of the neutron were slightly different. These calculations are phenomenally complex and model-dependent. Some studies have suggested that tweaking certain parameters could actually increase black hole production, which, if true, would falsify Smolin's central claim that our universe is optimized. Other analyses have been more supportive, but the overall picture remains inconclusive and hotly debated, lacking a definitive and universally accepted mathematical proof. Recent developments in fundamental physics have also cut both ways for the theory. The discovery of dark energy and the accelerating expansion of the universe presents a particular problem. A universe that expands at an accelerating rate is, in the very long term, a profoundly infertile one. Distant galaxies will eventually be pushed beyond each other's event horizons, and the formation of new black holes will cease entirely as matter becomes irreversibly diluted across an ever-growing void. If the goal of cosmic evolution is to maximize black hole production, then our universe's possession of dark energy seems like a catastrophic evolutionary misstep, a trait that would be strongly selected against. This is a difficult paradox for the theory to explain. On the other hand, advances in our understanding of black holes themselves, particularly through the work of physicists like Stephen Hawking and Leonard Susskind, have reinforced the idea that black holes are not simple dead ends. The laws of black hole thermodynamics and the ongoing mysteries of the information paradox highlight that we still have much to learn about their ultimate fate. This leaves a door open, however slightly, for unconventional ideas about what might happen to information and energy within them. Perhaps the most damning criticism, shared with other multiverse theories, is the challenge of testability and falsifiability. A scientific theory must make predictions that can, in principle, be proven wrong. While Smolin's theory does make some predictions such as the precise value of the maximum neutron star mass, these predictions are not unique to it. They can be explained by other models, and testing them requires extreme astrophysical precision that remains just out of reach. Furthermore, even if we never observe a universe being born from a black hole, a proponent could always argue that it happens in a realm forever beyond our observational reach. This ability to evade direct disproof moves the theory closer to the boundary of metaphysics. Critics argue that it risks becoming a just-so story, an elegant and intuitive narrative that explains what we see, but one that is ultimately untestable and therefore outside the strict bounds of empirical science. Its explanatory power is its greatest strength, but also its greatest weakness if that explanation cannot be pinned down and verified. Despite these formidable obstacles, cosmic natural selection has not been discarded. It retains a dedicated following and continues to stimulate valuable philosophical discussion about the nature of physical law. Its enduring appeal lies in its provision of a causal mechanism. Unlike the anthropic principle, which can feel like a philosophical shrug, or the multiverse, which relies on infinite randomness, Smolin's theory offers a dynamic process that happens within time. It provides a reason why the constants might be the way they are, framed in a language of competition, adaptation, and selection that is deeply familiar and intellectually satisfying. It represents a bold attempt to apply the most powerful known mechanism for creating complexity, natural selection, to the cosmos itself. While it may not be the final answer, it has irrevocably expanded the conversation, challenging us to consider that the rules of our universe may not be static decrees, but the living products of a grand evolutionary saga stretching across eons and realities beyond our own. But how seriously should we take this mind-bending possibility that we might be living in someone else's computer simulation? To evaluate Nick Bostrom's trilemma, we must first draw a crucial distinction between metaphysical possibility and genuine scientific plausibility. Something can be conceivable without being credible, and the simulation hypothesis sits right on this fascinating edge. Metaphysically, there's no logical contradiction in the idea. It doesn't violate any fundamental laws of logic to imagine an advanced civilization creating simulated realities. But moving from that abstract possibility to a scientifically plausible scenario requires us to grapple with the practical limitations imposed by physics and computation. And this is where the hypothesis encounters its most significant challenges. The most immediate hurdle is the staggering computational requirement, simulating an entire universe down to the quantum level, with its trillions of galaxies, each containing billions of stars and planets, is a task of such monumental scale that it defies our current understanding of physics and information theory. The number of calculations per second needed to simulate just the interactions within a single human brain is astronomically large, let alone an entire cosmos. Physicist Lisa Randall has been a vocal critic on these grounds, arguing that the energy and computational resources required would be so vast as to make the project practically impossible, even for a civilization thousands or millions of years more advanced than our own. She points out that the universe itself seems to impose fundamental limits on information processing limits like the Bekenstein bound, which restricts the amount of information that can be contained within a given volume of space. To simulate a universe as complex as our own, the simulating computer might need to be larger than the universe it's simulating, creating a paradoxical and seemingly insurmountable engineering problem. Beyond the sheer scale, there's the profound issue of infinite regression. If we are in a simulation, then what about the beings who created our simulation? Are they themselves simulated by an even more advanced civilization? This chain of simulations could extend backward infinitely, leading to a philosophical hall of mirrors with no ultimate base reality. This regress doesn't necessarily disprove the hypothesis, but it does undermine its explanatory power. If every reality is just a simulation within a simulation, we are still left with the original mystery of why there is something rather than nothing. We've just pushed the question of ultimate origin back one or an infinite number of steps. The hypothesis, in this sense, doesn't actually solve the problem of existence. It merely relocates it. Another critical question is motivation. Why would any civilization, no matter how advanced, embark on such an unimaginably vast project? Bostrom suggests possibilities like historical research, entertainment, or scientific experimentation, but each of these motivations comes with its own set of problems. If the goal is entertainment, would the simulation need to be so incredibly detailed and consistent across billions of light years? Wouldn't a much smaller, more efficient simulation suffice? For scientific research, creating a perfect simulation of a universe whose laws you are trying to understand might be circular. You'd essentially be creating a universe that operates by the rules you already programmed into it, which wouldn't necessarily teach you anything new about the nature of reality itself. These questions of motive aren't just philosophical quibbles. They speak to the practical likelihood that such a project would ever be undertaken, even if it were technically possible. Philosopher David Chalmers, while taking the simulation argument seriously as a modern version of Cartesian skepticism, introduces a crucial and sobering point. Even if we are in a simulation, it doesn't necessarily change the nature of our reality in any meaningful way. He argues that if the simulation is sufficiently detailed and consistent, then the objects within it, the chairs, stars, and people, are real for all practical purposes. Their existence is just as valid as they would be in a base reality. The laws of physics we discover would still be the real laws of our world, even if they are programmed. In this view, the question of whether we are in a simulation becomes almost trivial. It might be an interesting metaphysical fact, but it wouldn't alter the fundamental nature of our experience or the reality we interact with. A simulated glass of wine would still get you just as drunk, and a simulated falling rock would still hurt just as much. The reality we perceive would be, for all intents and purposes, genuine. So, is there any potential evidence that could distinguish a simulation from a base reality? Some theorists have suggested looking for potential glitches or shortcuts in the simulation, signs that the programmers took a computational shortcut. These might appear as subtle violations of known physical laws, unexpected quantization in otherwise continuous phenomena, or odd statistical anomalies in the constants of nature. Others have proposed that the very fact that our universe appears to be computable, that it can be described by mathematical laws, is itself suggestive of a simulation. Yet, these ideas remain highly speculative. Any observed glitch could simply be a new, undiscovered law of physics rather than evidence of a programmer. The search for evidence is fraught with the risk of confirmation bias, where we might interpret any unexplained phenomenon as proof of the simulation we already suspect. Despite these formidable critiques, the simulation hypothesis retains significant value. Its greatest contribution is not as a definitive answer, but as a powerful tool for questioning the very nature of reality. It forces us to examine our assumptions about what is real and what is possible. It challenges us to consider the deep connections between information, computation, and physical existence. In this sense, even if we are not in a simulation, the act of seriously considering the possibility expands our intellectual horizons and pushes the boundaries of cosmology and philosophy. It serves as a modern, technologically infused version of age-old questions about the reality of our experience, reminding us that our quest to understand the universe must always include a degree of humility about our own place within it and the potential limits of our perception. Yet this ancient intuition of purpose and design, seemingly banished to the realms of philosophy and theology by the rise of modern science, has found a powerful and surprising resurgence in the language of mathematics and physics. The discovery of cosmic fine-tuning has breathed new life into teleological arguments, moving them from the world of biological complexity, where natural selection provides a powerful non-teleological explanation, to the fundamental laws and constants that make any complexity possible in the first place. This isn't about finding a watch on a heath anymore. It's about discovering that the very metal from which all watches must be made has properties so exquisitely specific that the existence of any watch at all seems like a miracle. Modern teleology, therefore, doesn't argue from ignorance but from the precise, quantitative knowledge provided by cosmology and particle physics, shifting the debate onto entirely new ground. A leading voice in this modern revival is philosopher Robin Collins, who has refined the design argument using the rigorous tools of Bayesian probability. Bayesian analysis is a formal method of updating the probability of a hypothesis based on new evidence. Collins frames the argument not as absolute proof, but as a compelling inference to the best explanation. He asks us to consider two competing hypotheses. The first is the designer hypothesis, which posits that some form of intelligence or intentionality is behind the cosmos. The second is the single universe hypothesis, which asserts that our universe is a random, one-off occurrence with no deeper explanation for its constants. The evidence is the existence of a life-permitting universe. Collins argues that this evidence is enormously more probable if a cosmic designer exists than if our universe is merely a random accident. The incredible specificity of the constants, the need for them to fall within razor-thin margins, makes a life-permitting universe astronomically unlikely under the single-universe hypothesis. Under the designer hypothesis, however, the probability rises significantly because an intelligent agent could have reason or purpose to choose such parameters. Therefore, the discovery of fine-tuning should drastically increase our confidence that a designer exists. This approach avoids the classic God of the gaps charge by not inserting a designer where scientific explanation is currently lacking, but instead by interpreting the entire scientific framework, the shocking specificity of its foundational rules, as evidence that points beyond a purely materialistic origin. This sophisticated probabilistic argument, however, faces formidable objections from the scientific community. The most prominent counterargument comes from the multiverse hypothesis. If an infinite or near-infinite number of universes exist, each with randomly different physical constants, then it becomes statistically inevitable that at least one universe will have the right combination for life. We shouldn't be surprised to find ourselves in that universe. We couldn't exist anywhere else. In this view, the appearance of design is an illusion created by a profound selection effect. The multiverse acts as a kind of cosmic lottery where every possible ticket is printed. While almost all are losers, a few will inevitably be jackpot winners, and it is no mystery that we hold a winning ticket. This provides a purely physicalist explanation for fine-tuning that renders a designer superfluous. Why invoke a mysterious intelligence when an infinite ensemble of universes can do the explanatory work? Proponents of this view argue it is more parsimonious, adhering to a principle of seeking the simplest explanation without unnecessary entities. Yet, the multiverse rebuttal itself faces a powerful meta-critique, often called the problem of divine fine-tuning or the challenge of necessary existence. Critics of the multiverse point out that the mechanism that generates this vast ensemble, be it eternal inflation, string theory landscape, or another process, must itself operate according to a specific set of meta-laws. These laws govern how universes are spawned, what range of constants they can have, and the overall structure of the multiverse. For this mechanism to produce even one life-permitting universe, its own governing principles must be finely tuned. Why does the inflationary field have the specific potential that allows for bubble universes? Why does the string theory landscape permit stable universes at all? This line of reasoning suggests that the multiverse doesn't actually solve the fine-tuning problem. It simply pushes it back one step from the constants within universes to the laws that govern the multiverse-generating mechanism. One could then argue that a designer is needed to explain the fine-tuned meta-laws of the multiverse, leading to an infinite regress. Alternatively, some argue that these meta-laws must exist necessarily, that they could not have been otherwise. This idea of a necessary existence, a universe or multiverse whose fundamental nature is logically inevitable, becomes another competing explanation that seeks to avoid both design and chance. This fascinating debate has also spurred the development of alternative naturalistic accounts of teleology that seek a middle path. Some philosophers and physicists explore the idea that purpose or goal-directedness might be a fundamental, emergent property of complex systems, not requiring a designer but arising naturally from the laws of physics themselves. Could the universe have an inherent tendency toward complexity and consciousness? This is not a claim about a conscious creator, but rather a proposal that the cosmos has an intrinsic directionality, a telos built into its very fabric that guides it toward states of increasing order and awareness. Others look to principles in quantum mechanics or information theory that might suggest a form of causality that operates backward in time or from the whole to the parts, providing a physical basis for goal-directed behavior without invoking the supernatural. These ideas are highly speculative but represent a creative attempt to grapple with the persistent intuition of purpose in a way that remains within the bounds of natural science, acknowledging the evidence of fine-tuning while seeking an explanation that doesn't rely on a transcendent intelligence. The conversation has thus evolved into a rich and nuanced exploration of causality, probability, and the very nature of explanation itself, demonstrating how an ancient philosophical question has been transformed and deepened by the startling discoveries of modern cosmology. What if consciousness isn't a rare and fragile flame flickering in the darkness of an unconscious universe, but rather the very ground of being itself, the fundamental substance from which all reality emerges? This is the radical and awe-inspiring proposition of consciousness-based approaches to cosmology, a perspective that turns traditional physicalism completely on its head. Instead of asking how lumps of unconscious matter somehow generated mind, these theories suggest that consciousness is primary, and the physical world as we know it is a manifestation or representation of conscious experience. It's a view that echoes ancient philosophical traditions but is now being articulated with the precise language of modern mathematics and neuroscience, offering a breathtakingly different answer to why our universe has the specific rules that it does. At the forefront of this effort is neuroscientist Giulio Tononi's Integrated Information Theory, or IIT. This isn't just another theory about the brain. It's a fundamental framework for understanding what consciousness is and how it arises from any system. IIT proposes that consciousness is identical to a system's capacity for integrated information, measured by a quantity called phi. The core idea is that consciousness isn't about what a system is made of, but how its components are organized and interconnected. A system has high phi if it is both highly differentiated with many possible states and highly integrated, meaning these states can't be reduced to the sum of independent parts. Your brain, with its trillions of synapses forming an incredibly complex and unified network, has very high phi. A rock whose atoms are only weakly connected has very low phi. A digital camera sensor has many differentiated pixels, but they aren't integrated. Each pixel operates independently, so it has no true consciousness, only a collection of isolated data points. IIT provides a way to quantify the inner life of any system, from a human to a computer to a simple circuit, based purely on its causal structure. The cosmological implications of this idea are nothing short of revolutionary. If consciousness is integrated information, then the laws of physics might not be arbitrary rules, but could be the way they are precisely because they allow for the emergence of systems with high phi. The universe's constants could be fine-tuned not for life in a general sense, but for the specific kind of complex, integrated structures that can support a rich inner experience. The strength of the forces, the stability of atoms, the existence of long-lived stars all might be prerequisites for building systems capable of substantial integration of information. In this view, the universe isn't a cold, empty machine. It's a vast, evolving network gradually increasing its capacity for consciousness. The ultimate purpose or direction of cosmic evolution might be to maximize integrated information, to create ever more complex and unified states of being. This suggests a cosmos that is not blind but is, in some profound sense, feeling its way toward greater awareness, with us as one of its most articulate expressions so far. This perspective finds a powerful ally in the work of Christoph Koch, a leading neuroscientist and a prominent advocate for panpsychism. the view that consciousness is a universal and fundamental feature of all matter. Koch, who collaborated closely with Tononi, argues that IIT naturally leads to a form of panpsychism. If consciousness is indeed a property of any system with integrated information, then it isn't unique to brains. While a rock or a thermostat would have a vanishingly small amount of phi, they would not be completely devoid of experience. They would possess a faint whisper of consciousness, a simple, raw feeling of existence. This isn't to say an electron is thinking. It's to suggest that experience itself might be a fundamental property, much like mass or charge, that is present to some degree in all things. The complex, vivid consciousness of a human being would then emerge from the incredibly sophisticated integration of these fundamental conscious units within our brains. This elegantly sidesteps the infamous, hard problem of consciousness, the question of how subjective experience arises from objective matter, by proposing that experience was never generated in the first place. It was always there, and complex consciousness is simply what happens when fundamental consciousness is organized in incredibly intricate ways. This line of thinking leads to a truly cosmic form of panpsychism. Perhaps the entire universe, as a single, causally connected system, has its own form of cosmic consciousness. This isn't a personal God, but a vast, slow, and alien form of experience that arises from the total integrated information of the cosmos. The galaxies, stars, and dark matter webs could be the neurons of this cosmic brain, with their gravitational and quantum interactions constituting its thoughts. This idea, while seemingly outlandish, is being explored by serious physicists and philosophers as a way to make sense of the universe's apparent fine-tuning. If the cosmos has an innate capacity for consciousness, then its laws might be structured to nurture and maximize that capacity. The universe's constants are what they are because these values allow for the richest possible tapestry of conscious experience to unfold across space and time. Of course, these consciousness-based approaches face significant scientific criticisms and testability challenges. The most common objection is that they seem to border on the mystical or non-scientific. How do you measure phi in a human brain, let alone in a star system? While IIT offers a mathematical framework, actually calculating phi for anything but the simplest systems is currently computationally impossible. Furthermore, critics argue that these theories don't yet make specific, unique predictions that can distinguish them from more conventional physicalist explanations. Why should the laws of physics that maximize integrated information be the same ones that allow for stable atoms and long-lived stars? The connection, while intuitively appealing, remains speculative. There is also the combination problem. If elementary particles have a tiny amount of consciousness, how do they combine to form our unified stream of experience? Explaining how micro-experiences merge into macro-experiences is just as challenging as explaining how non-experience becomes experience. Despite these challenges, the value of consciousness-based approaches is immense. They force a radical expansion of our conceptual horizons, challenging the materialist assumption that has dominated science for centuries. They take the one thing we know for certain, that experience exists, and place it at the very center of our quest to understand reality. This isn't a retreat into mystery. It's an attempt to build a more complete science, one that can account for the interiority of the world as well as its exterior behavior. By suggesting that the universe's rules might be optimized for the growth of consciousness, these theories offer a powerful narrative of meaning and purpose that is deeply lacking in many other cosmological models. They present a vision of a universe that is not just described by mathematics, but is also felt, experienced, and perhaps even, in its own way, awake. A cosmos where the emergence of beings who can wonder about its origins is not a random accident, but the fulfillment of its most fundamental nature. What if the most fundamental laws of physics aren't immutable commandments etched into the fabric of the cosmos, but are instead more like living, breathing entities that themselves change and adapt over time? This radical idea challenges one of the deepest assumptions in all of science, the belief that the rules of the game are fixed for all eternity. For centuries, from Newton to Einstein, physicists have operated under the paradigm that the laws of nature are eternal and unchanging, the same everywhere and everyone. But what if we've been misled by this Platonic ideal? What if the universe is not a static, finished product, but an ongoing process, a work in progress whose very rules are still being written? This notion of evolving laws pushes us to consider a cosmos that is not just governed by time, but is fundamentally shaped by it, a reality where causality itself might be more fluid and participatory than we ever imagined. The seeds of this revolutionary thinking were planted by the brilliant and unconventional physicist John Archibald Wheeler. Best known for coining the term black hole, Wheeler ventured into even deeper philosophical territory with his concept of participatory anthropism. He famously suggested that we are not merely observers of the universe, but participants in its creation, and that the act of observation itself might play a role in bringing specific physical realities into being. Wheeler took this a step further by proposing that the laws of physics might not be pre-existing, but could have somehow emerged or crystallized in the early universe. He even speculated that these laws could continue to evolve through an ongoing dialogue with the conscious beings that observe them. In Wheeler's vision, the universe is a self-excited circuit, a closed loop where the observers are inextricably linked to the observed, collectively shaping the reality we measure. This is a dramatic departure from the classical view of a detached scientist studying a fixed, external world. It suggests a cosmos that learns about itself through its inhabitants, a universe that is becoming rather than simply being, with its laws potentially evolving as part of that grand cosmic process of self-discovery. This philosophical framework finds a more concrete, though still speculative, expression in the work of physicists exploring the possibility of varying physical constants. The idea is audaciously simple. What if the so-called constants of nature, like the speed of light or the strength of gravity, aren't actually constant at all? What if they change over cosmological timescales, slowly drifting from their values in the early universe to what we measure today? Theories that propose such variation are not merely philosophical musings, they make specific, testable predictions. For instance, if the fine structure constant, which governs the strength of electromagnetic interactions, were different in the distant past, it would leave a detectable imprint on the light from ancient quasars. Some astronomical observations have even hinted at such a signal, though the results remain controversial and hotly debated. If confirmed, varying constants would represent a monumental shift in our understanding. The universe's rulebook would not be a fixed, eternal document, but a living text with its most fundamental parameters subject to revision across billions of years. This would imply a cosmos with a history and a future that are not just about the rearrangement of matter under fixed laws, but about the evolution of the laws themselves, a truly dynamic and historical reality at its most fundamental level. The plot thickens considerably when we consider the most cutting-edge approaches to quantum gravity, where time itself becomes an emergent property rather than a fundamental background. In theories like loop quantum gravity and causal set theory, the smooth, continuous flow of time we experience is not a primary feature of reality. Instead, it is an approximation that arises from the collective behavior of more basic, timeless entities, loops of space or discrete events in a causal network. If time is emergent, then it becomes much harder to sustain the idea of eternal, timeless laws. Laws that are outside of time require time to be fundamental. If time is not fundamental, then the laws themselves must be part of the emergent reality, and what emerges can potentially change and evolve. This turns the traditional hierarchy completely on its head. We normally think of time unfolding within a fixed arena of physical law. But if time is emergent, then the laws themselves must unfold within time, or whatever process gives rise to our experience of temporal flow. This suggests a universe where the rules are not written in stone, but are more like habits that have formed over the deep history of the cosmos, patterns of behavior that have become stable and reliable but could, in principle, have been different and might still be subject to change. This line of thinking is powerfully developed in Lee Smollen's later work on what he calls temporal naturalism. Building on his earlier theory of cosmic natural selection, Smollen argues that we must take the reality of time with utmost seriousness. In his view, the belief in eternal, timeless laws is a kind of philosophical hangover from Plato, a prejudice that has hindered our progress in theoretical physics. Temporal naturalism posits that everything that is real, including the laws of nature, exists in time. There is no timeless realm of perfect mathematical forms. There is only the present moment and its relationship to the past and the future. In this framework, the laws of physics are not exceptions to time's flow. They are aspects of it. They could have been different in the past and could change in the future. They might even be subject to a form of evolution, not necessarily through the mechanism of universe reproduction via black holes, but through a more general process of cosmic learning and adaptation. This is a profoundly radical departure from the foundation of modern science, suggesting that the quest for a final, immutable theory of everything is a mirage. Instead, we might be living in a universe whose rules are still settling into place, a cosmos that is literally inventing itself as it goes along, with every moment holding the potential for genuine novelty. A similarly dynamic view of reality emerges from Carlo Rovelli's relational quantum mechanics. Rovelli challenges the idea of an absolute, observer-independent reality. In his relational interpretation, properties of objects only exist in relation to other objects. There is no meaning to the state of a system in isolation. Reality is constituted entirely by the web of relationships between things. This has profound implications for the laws of physics. If properties are relational and not absolute, then the laws that govern those properties might also be relational. A law would not be a divine decree, but a summary of the consistent ways that things interact with each other within the network of reality. This relational view naturally accommodates the possibility of change. As the universe evolves and new relationships form, as new particles interact, new structures coalesce, and new observers emerge to measure the world, the effective laws that describe these interactions could themselves evolve. The stability of the laws we observe might not be a sign of their eternity, but simply a reflection of the fact that the universe has settled into a stable set of relationships at the scales we can observe. At the deepest levels or in the most extreme conditions, the relational network might be more fluid, allowing for a more fundamental plasticity in the rules that govern existence. To grasp this concept of evolving laws, consider a powerful metaphor from the world of ecology. The behavior of a complex ecosystem, like a rainforest, is governed by a set of rules: predator-prey relationships, nutrient cycles, symbiotic partnerships. These rules are not written down anywhere. They emerge from the interactions of countless organisms over time. Furthermore, these rules can and do change. The introduction of a new species, a change in climate, or a catastrophic event can rewrite the rulebook, leading to a new stable set of relationships. Now, imagine the entire cosmos as the ultimate complex system. The laws of physics we measure might be the stable, emergent habits of a universe that has settled into a particular mode of being after 14 billion years of evolution and interaction. But this cosmic ecosystem could, in principle, undergo phase transitions or shifts that alter its fundamental rules, moving it to a new stable state with a different set of physical constants and laws. We may simply be living during a long, stable epoch where the rules appear fixed, unaware that the cosmos has a much richer and more dynamic legal history and future than we can possibly imagine from our limited temporal vantage point. This vision of a learning, adapting cosmos offers a breathtakingly new narrative for our place in the universe, not as passive observers of eternal truths, but as active participants in an unfinished and ever-evolving reality. Throughout the long and storied history of physics, a surprising and somewhat mysterious guide has often pointed the way toward profound discovery, a deep sense of mathematical beauty. The legendary physicist Paul Dirac gave voice to this principle with his famous declaration that it is more important to have beauty in one's equations than to have them fit experiment. He argued that while an initial disagreement with observation might simply be due to minor complexities not yet understood, a fundamental lack of elegance in the mathematics was a far more serious flaw, suggesting the theory was likely wrong at its core. This might sound like a strangely subjective compass for the most objective of sciences, but time and again, this faith in mathematical beauty has been spectacularly vindicated, leading to breakthroughs that reshaped our understanding of reality. Dirac's own work stands as a monumental testament to this idea. While crafting the quantum mechanical equation for the electron, he was obsessed with making it mathematically beautiful, demanding it be linear and respect the principles of special relativity. The result was an equation of stunning elegance, but it came with a bizarre and unwelcome prediction. It suggested the existence of a mysterious particle with the same mass as an electron but with opposite charge. At the time, no such particle was known, and it could have been dismissed as a mathematical artifact, a useless but pretty consequence of the algebra. Yet Dirac trusted the beauty of his equation. He boldly proposed the existence of this new particle, which he called an anti-electron. Just a few years later, Carl Anderson discovered this exact particle in cosmic ray experiments, and we now know it as the positron. Dirac's equation didn't just predict a new particle, it unveiled a fundamental symmetry of nature, revealing that for every particle, there exists an antiparticle, a truth that was first glimpsed not in a cloud chamber, but in the compelling elegance of a mathematical formula. This pattern of beauty leading the way repeats itself throughout 20th century physics. Einstein's general theory of relativity is another masterpiece of mathematical aesthetics. He was guided not by a specific experimental anomaly, but by a profound belief that the laws of physics should be elegantly expressed and independent of any arbitrary coordinate system. His quest for a theory that was generally covariant led him to the mathematics of Riemannian geometry, and the resulting field equations are renowned for their powerful simplicity and depth. When he first saw the final form of his equation, which describes gravity as the curvature of spacetime, he is said to have been deeply concerned that it might not be compatible with the conservation of energy. He soon realized, to his immense satisfaction, that the equation's beautiful mathematical structure automatically guaranteed that energy was conserved. The theory's aesthetic coherence was a sign of its truth, a feature that has been confirmed by every experimental test for over a century. In the world of particle physics, this pursuit of beauty often takes the form of a principle called naturalness. The concept suggests that the fundamental parameters of the universe should be of order 1. There should be no inexplicably large or small numbers in our core equations. A naturally beautiful theory wouldn't require miraculous, precise cancellations between enormous numbers to produce the delicate constants we observe. This drive for naturalness was a major motivation for proposing supersymmetry, a theory that elegantly solves the hierarchy problem by positing a symmetric partner for every known particle. The idea is profoundly beautiful, restoring a mathematical balance between the families of particles known as fermions and bosons. Yet, as we've discussed, the stubborn refusal of these superpartners to appear at the Large Hadron Collider has forced a painful reconsideration. The universe, it seems, might not share our human preference for this particular kind of mathematical elegance, leaving physicists to grapple with the possibility of an unnatural universe where fine-tuning is simply a brute fact. This tension raises a critical and humbling question. Are we discovering a beauty inherent to the cosmos, or are we merely projecting our own cognitive preferences onto it? Our sense of mathematical beauty, our appreciation for symmetry, simplicity, and elegance is undeniably shaped by the evolutionary path of the human brain. We are pattern-recognizing creatures who find satisfaction in order and harmony. It is entirely possible that these preferences have served as effective heuristics for navigating a complex world, and that they now serve us equally well in constructing scientific models. But we must remain open to the possibility that the universe's ultimate rules might be beautiful in a way that is completely foreign to us, a form of elegance so alien that we might initially perceive it as ugly or arbitrary. The history of science shows that our concepts of beauty evolve. The quantum mechanics that so many founding fathers found deeply distasteful and unsettling is now celebrated for its own strange and non-intuitive beauty by contemporary physicists. The true laws of nature may not conform to our current aesthetic tastes, but they will undoubtedly possess a deep and compelling logic that, once understood, we will learn to recognize as a new and more profound form of beauty. This ongoing dialogue between human intuition and cosmic reality is one of the most fascinating aspects of the scientific journey, a reminder that in our search for the rules that weren't written, we are also deciphering the limits and potentials of our own minds. Perhaps the true nature of our universe's rulebook is not a single, elegant equation waiting to be discovered, but a complex tapestry woven from multiple, overlapping threads of explanation. After all, we don't explain the existence of a thriving rainforest by pointing to a single cause. We understand it as the interplay of sunlight, rainfall, soil chemistry, evolutionary history, and countless other factors. Why should the cosmos itself be any simpler? This is the power of a synthetic approach, which acknowledges that the profound mystery of cosmic fine-tuning might require not one solution, but a combination of several. Instead of forcing a choice between the multiverse, a designer, or fundamental mathematical necessity, we can consider how these ideas might work in concert, each explaining a different piece of the puzzle and compensating for the weaknesses of the others. This integrated perspective doesn't seek an oversimplified answer. It embraces the inherent complexity of reality, suggesting that the universe's parameters are the result of a layered, multi-causal process. We can begin to construct this synthesis by considering a powerful sequence. Imagine first that a vast multiverse does exist, generated by mechanisms like eternal inflation. This provides the raw statistical material, a near-infinite array of possibilities where every conceivable set of physical constants is realized somewhere. This alone, however, is a rather empty explanation. It's like having a library containing every possible book. It guarantees that a specific text exists, but it doesn't explain the grammar, plot, or beauty of the one you're holding. This is where other principles come into play. Within this vast cosmic library, anthropic selection acts as a filter. We can only find ourselves in a universe compatible with our existence as observers. This explains why we observe fine-tuning, but not why a life-permitting universe was on the shelf in the first place. To answer that, we might then add a third layer: fundamental mathematical principles that constrain the range of possible universes the multiverse can generate. Perhaps the multiverse isn't completely lawless. Its own meta-laws, the rules that govern the inflationary field or the string theory landscape, are themselves shaped by deep mathematical necessities that favor certain types of structures. In this view, the multiverse provides the lottery, anthropic selection explains why we hold a winning ticket, and fundamental mathematical beauty explains why the lottery had prizes worth winning at all. This kind of integrated thinking is exemplified in the work of visionary physicists like David Deutsch and his development of constructor theory. This framework shifts the focus from what happens to what can or cannot happen, from the dynamics of particles to the realm of possible physical transformations. Constructor theory asks what tasks can be performed by a physical entity, a constructor, without itself being permanently changed in the process. In this view, the laws of physics are fundamentally about which transformations are possible and which are impossible. This provides a new language for synthesizing explanations. The fine-tuned constants we observe could be understood as the necessary conditions for the possibility of constructing complex, information-processing entities like ourselves. The laws aren't just a list of numbers, they are the rules that make certain cosmic projects like the construction of a star, a planet, or a conscious mind possible or impossible. This doesn't necessarily explain why these are the rules, but it reframes the question in a more powerful way, connecting the existence of observers directly to the universe's operational capabilities. We can further enrich this synthesis by carefully integrating the insights of philosophers like Nick Bostrom on observation selection effects. This is a more formal and generalized version of the anthropic principle. It provides a rigorous mathematical framework for how to reason about what we should expect to observe, given that our existence is contingent on being in a universe that allows for observers. When combined with other theories, it acts as a crucial corrective lens. For instance, it helps us navigate the measure problem of the multiverse or the Boltzmann brain paradox by forcing us to be precise about the reference class of observers we belong to and the conditional probabilities involved. It tells us that if a theory predicts that the vast majority of conscious experiences are of a certain type like disembodied Boltzmann brains with false memories, then we should be deeply skeptical of that theory, as it renders our own coherent experience highly atypical. This isn't a standalone answer, but a vital tool for evaluating which synthetic combinations of explanations are actually plausible and coherent from our specific vantage point. Ultimately, adopting a synthetic approach is an admission that we may be asking the wrong question by seeking a single, silver bullet solution. The universe is under no obligation to conform to our human desire for simplicity or our aesthetic preference for elegant, monolithic theories. Its history is likely one of contingent, layered emergence, where the laws we see today are the result of a complex chain of events, perhaps a fundamental mathematical structure giving rise to a generative mechanism like inflation, which in turn spawns a multiverse of possibilities within which anthropic selection operates, all leading to a universe capable of supporting complex constructs. Can comprehend the process, this layered view doesn't diminish the wonder, it amplifies it. The cosmos becomes a richer, more intricate, and more fascinating place when we recognize that its rules may be the product of a grand, collaborative effort between chance, necessity, and the fundamental possibility of observation itself. And so our journey brings us to a moment of profound reflection, standing at the edge of a vast ocean of understanding, humbled by its depth. We have ventured through an extraordinary landscape of ideas, from the cosmic lottery of the multiverse to the evolutionary forge of black hole births, from the silent, eternal realm of mathematical structures to the startling possibility of a programmed simulation. Each theory, in its own way, offers a compelling lens through which to view the central mystery. Why does our universe play by this specific, life-permitting set of rules? Yet as we hold these lenses up to the light, we must acknowledge that none provides a perfect, complete picture. The multiverse explains the odds but feels untestable. Cosmic natural selection offers a mechanism but lacks evidence. The mathematical universe is elegant but struggles with consciousness. The simulation hypothesis is technologically intriguing but philosophically fraught. They are all brilliant, partial sketches of a truth that remains tantalizingly out of focus. This is not a failure of science, but rather a testament to the sheer grandeur of the question itself. The quest to understand why the constants are fine-tuned, why the laws are so mathematically beautiful, and why reality is even comprehensible at all, represents the final and most ambitious frontier of human curiosity. It pushes at the very limits of what we can observe, test, and even imagine. This enduring mystery is an open invitation, a reminder that the universe is not a puzzle to be solved and filed away, but a living, breathing question that continues to challenge and inspire generation after generation. It calls us not to passive acceptance but to active wonder and participation. As Albert Einstein so beautifully put it, the most incomprehensible thing about the universe is that it is comprehensible. The fact that we can even pose these questions, that our minds can grapple with the deepest fabric of reality, is a miracle in itself. So let this not be an end, but a beginning. Let it fuel your own sense of wonder. Follow the new discoveries from telescopes and particle colliders. Read about the debates among cosmologists and philosophers, and never stop asking why. For in that collective, ongoing pursuit of understanding through education, through engagement, and through simple, rapturous awe at the night sky, we truly honor the profound and magnificent mystery of a universe that chose, for reasons we may never fully know, to allow for our existence. But our exploration doesn't have to end here. If these cosmic mysteries have sparked your curiosity, there are so many ways to keep that sense of wonder alive and burning brightly. Right here on this channel, we're constantly diving into the deepest questions about our reality, from the nature of black holes to the search for alien life. Hitting that subscribe button and turning on notifications is the easiest way to ensure you don't miss our next journey to the edge of understanding. I've also packed the video description with a treasure trove of resources to fuel your own exploration, links to groundbreaking books by thinkers like Max Tegmark and Brian Greene, documentaries that bring these concepts to life, and links to websites that track the latest discoveries in cosmology and particle physics in real time. This conversation is far from over, and your perspective is a vital part of it. Scroll down and share your thoughts in the comments. Which explanation for our universe's fine-tuned rules resonates most deeply with you? Do you find the multiverse idea compelling, or does cosmic natural selection feel more elegant? Perhaps you have your own unique theory. This is one of the most profound discussions humanity can have, and I read every single comment, learning from your insights and perspectives. To truly wrap your mind around the scale of these ideas, nothing compares to a visit to a local planetarium or science museum. Standing under a dome that recreates the vastness of the cosmos, seeing the intricate dance of galaxies and the life cycle of stars, transforms these abstract concepts into a visceral, awe-inspiring experience. It's a powerful reminder that we are part of something incomprehensibly vast and beautiful. Make a point to follow the incredible work being done by organizations like NASA, the European Space Agency, and CERN. The images from the James Webb Space Telescope aren't just pretty pictures, they are raw data, helping us test these very theories about the early universe. The experiments at the Large Hadron Collider are probing the fundamental rules of reality itself. By following their social media channels or newsletters, you become a direct witness to the unfolding story of human discovery, watching as we collectively piece together the puzzle of our existence. Remember that this isn't just a quest for scientists in lab coats. Philosophy plays an equally crucial role. Engaging with the works of ancient thinkers like Plato and Aristotle, or modern philosophers like Nick Bostrom and David Chalmers, allows us to grapple with the meaning behind the math, helping us interpret what these scientific discoveries tell us about our place in the grand scheme of things. This enduring drive to question, to explore, to look up at the starry sky and ask why, is one of the most defining and noble aspects of our species. It connects us to every human who has ever wondered about the lights in the heavens. That curiosity is a gift, and nurturing it is how we honor our role as conscious inhabitants of an astonishing and mysterious cosmos. So keep wondering, keep learning, and keep looking up. The universe has written its rules in a language we are still learning to read, and every one of us is invited to be a student in its magnificent, never